fusion is very fast. This is good for the nanomaterial, doping nanomaterial. Okay, next one. What the mechanism of this reaction? Okay, maybe this is a new type solid acid-solid base reaction, neutralization. Yes, okay. So and this speed is a very high speed. So and this overcomes the slow diffusion of the interface. Okay, surface is a very high energy state, so the diffusion is very easy. So this is a very general and powerful techniques to synthesize a nanomaterial. Okay, this is one of the small part of the synthesizable and ceramics material. Okay, lithium phosphate, solid electrolyte, lithium silicate, CO2 absorber, strontium tungstate, phosphor material. So okay, KSF and visible driven hot catalyst, barium titanate is a king of electroceramics. Okay, so also silicate. This is also famous phosphor material. So okay, and cesium, zirconium, hafnium chloride. This is a very good scintillator. Maybe yesterday, and Professor Kurosawa talked, the scintillator material. This material can be easily synthesized by this technique. Bismuth vanadate, yellow pigment, so lithium ion battery, the cathode material is also can be synthesized this technique. Okay, so, and Professor Yamamoto said, diversity of phosphor material, this is important. Only strong lion in the flat savanna. Only lion, only lion, only lion. This is not abnormal. Lion means nitride. Only nitride, 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 nitride. This is very abnormal. Big five, another small animal in flat savanna. This is a normal state. Okay, and so this is mean and some dream and reality. Dream means future promising material. Reality is business available and material. So one of the very promising dream is perovskite. Many people research perovskite quantum dot material. So okay, but quantum dot material to synthesis technique is very severe and very precise one. Hot injection. So maybe 1 gram, 2 gram, and your student make 1 gram QD. This is okay, but 100 kilogram QD synthesis, this is not easy. Especially in the company makes 10 kilogram, 100 kilogram. This is very difficult. Okay, our technique, final product is always a nano-size material because cracking, high energy state, and so high energy state makes a very small, well crystalline nanocrystalline. Always the final product is a 5 nanometer size nanocrystalline. Okay, so this is one of the WSS technique. In inert argon atmosphere and no addition water case, this is a very simple and a mixture of raw material. But with a small amount of water, we can see the single phase perovskite material. This is a nanocrystallite. Only simple and mixing that we can get very small nanocrystal. Okay, this is one of the movie. Many people strongly claim mechanical milling technique. No, only shaking. Shaking is mechanochemical reaction. Maybe a no. Only simple mixing in pressure cooker, 80 degrees, 80% the humid air. That we can get the very well crystalline perovskite material. This is a brom, cesium, lead, Pb, and the bromide perovskite material. Okay, it's very easy. So final product is a little bit aggregated and powders. But okay, this aggregation is very weak. We can easily dispose of by the addition of some surfactant. Okay, so this is our sample data. Okay, bromide is very strong and green emissive and perovskite material. Very simple technique. This is almost comparable to the commercial perovskite QD material. Okay, but this is only dream. Always final product is a nanocrystal. Nanocrystal is not practical material. Practical LED phosphor is a very big size and from 10 and 20 micrometer size one. Your technique is only nanomaterial. Electroceramics application is maybe good. Yes, okay. We can overcome such a problem, especially KSF. KSF is commercially available red phosphor material. Your smartphone, your TV, you always use KSF material for red component. Okay, this is a very typical techniques of KSF synthesis. Okay, silica plus and HF. HF, okay, very simple technique, but HF is very dangerous, especially your student use HF. Oh, this is a very dangerous. Okay, so sometimes the company people have injury by HF. So especially in Korea, very famous and venture phosphor maker have some trouble in the KSF synthesis so by this HF material. Okay, this is a very simple data of the WSSR synthesis KSF. Okay, we use silica, always simple potassium fluoride with a small amount of acid solution. Okay, but the acid is a very safety. No solution is not important. This direct silica to and KSF transformation easily possible to prepare such a behavior. So okay, HCl, acetic acid. Okay, maybe I feel acetic acid is more safety, but my student don't try because they said very safety, but the smell is a little bit strong and called sushi process. Okay, this is very simple and stirring in the acid solution. We can get KSF material. This is a simulation pattern of KSF. Okay, we can get. Okay, and for the water, only water case and a very slow reaction of KSF synthesis. But okay, because in water acid addition is effective for to synthesize this material. So because the WSSR technique is neutralization between the solid acid and the solid base. Very strong acid condition or very strong and basic condition is not good and very slow. Okay, this is one of the movie file. KMF HCl solution. We are adding silica particle. And the blue LED radiation. Okay, this is a real-time movie. You can see the silica powder. no solution. You can see red light emitting KSF material. Only 1 minute and the mixing is enough to synthesize the material. Okay, acid is important, so not so important. This is only control of the pH, only neutralization. So sometimes we use only simple and silica plus and KF and ammonium fluoride. Why ammonium fluoride? This is a very near the neutrality. Only KF case and strong the basic condition. This is not good. We need acid addition and pH control. Okay. This is only 1 hour, 2 hour, 4 hour. Okay. You can see the KSF materials peak. So most of the researchers use HF. So because the silica is required for the synthesis KSF, this and the oxygen and the fluoride and the exchange need a solution. No, only simple the solid state reaction. So water-rich solid state reaction. This means. Okay, but you use a solution. This is a solution technique. No, and we can also use a really solid state reaction. Only simple and raw materials and KMF, mangan, potassium mangan fluoride and acid solution, and so we added and the whole day and 1 month and keeping on the and your aluminum boat, we can get KSF material. But this emission intensity is not so high. Why? Because very small particle. Solid state reaction case is final product is a very small size particle. This is not good for practical application. Practical application needs a very large size, over 10 micrometer size material. So finally, we optimize synthesis technique for the KSF material. We use HCl solution with a small amount of potassium fluoride and potassium mangan fluoride. This is a manganese source. And another one is only hydrochloric and silica acid solution, and a very slow addition of reaction. Why is the solution and the solution? Very slow addition rate. So this means we control the nucleation. Very slow nucleation. There's a small amount of the nucleation. So final product is a more bigger, larger one. Okay. Because the KMF needs acid, and so fluoride concentration. So only under acid with fluoride containing the solution. This case and the KMF solution is stable. So only simple and mixing and very small amount of DL and water poor WSS technique is a final product is brown. So easily decompose to the mangan O2. So we use acid solution and acid solution. Very water-rich WSSR technique. Okay, the very and highly amount and solution and solvent case, and we can get a final bigger size crystal of KSF material. Okay. This is the same image of our synthesized KSF. Okay, you can see the very small size triangle the morphology nanocrystal. So this is maybe a simple and jigsaw puzzle of nanocrystal. Nanocrystal makes epitaxial-like and crystal growth. The final product is a very beautiful large size KSF material. This size, over 10 micrometer, this is a very good for the practical application. Okay. This shows the same image of KSF material. Okay, this is our sample. So this is a commercial sample, UJL. UJL is a Korean phosphor company, and they bought Samsung's phosphor business. Okay, this means that this material is come from Samsung. Okay, sorry, and the scale is a little bit different. So our sample is at maybe under 10 micrometer. The commercial one is 20 micrometer size one. Okay. Finally, and this is a best condition to synthesize the material. 7 more % and manganese doped one is the best. So blue one is a UJL sample. Black one is our synthesizer samples. Almost 103 from 103 to 105% luminescence intensity compared to the Samsung samples. Okay, this is maybe a business available luminescence intensity. My student do it. Maybe the company people more serious under optimization. Maybe okay, more higher luminescence intensity. And so we use acetic acid, phosphoric acid, and all acid is okay. HCl is also okay. So this is a very easy, very safety to synthesize a KSF material. Okay, let me summarize my talk. Okay, and slow reaction. Conventional ceramic solid-state reaction is need a high temperature and a very long time. And this is but not a true story. And a very easy synthesize water-assisted solid-state reaction. And so this is not mechanochemical reaction, and this is not hydrothermal reaction and solution reaction. So this is solid-state reaction accelerated by the small amount of water. Water maybe act as a OH group, surface and very strongly chemi-solved OH groups. This enhances the surface of the solid acid and the solid base ability. Okay. Okay. Hydrothermal. Most of the hydrothermal and most of the mechanochemical reaction is such a very simple solid-state reaction. Okay. Oh, final one. Okay, mixed raw material. Very simple, and the plastic bottle and the glass bottle, very low temperature synthesis is easy. Low temperature process. Okay, this means you have a bamboo and a steamer in your kitchen. This means you can continue the research works in your home kitchen after retirement from company or university. Okay, thank you for your kind attention. 谢谢.
Thank you very much. That's a very nice talk. Any questions?
Thank you for Toda Sensei. Nice talk. So usually we wonder can we control the concentration of the dopant and uniformly of dopant inside or outside particles, so that balance of the dopant. Please take us the comment on my
Okay,
questions.
and the surface area is very highly energy state. We cannot say temperature. Temperature means a very large volume size and average of energy state. But this very high energy state is only surface, very nano areas activation of the energy. So, but this means final product is cracking and a very small size. The surface is a very high energy state. So surface penetration is the most slow process into the nano size material. So maybe this is good for the doping case. But I don't check the real and penetration mechanism to nanomaterial. But always I check NMR and some another analysis technique. Okay, and very small size, but doping and manganese and lanthanide and other doping material is very homogeneous. Small particle, but homogeneous. This is very strange and for me. And the mechanism check is also important next research works.
All the reactions occur in normal condition or in a glove box with a special...
No. In only in humid air, so the only air synthesis is also okay. So, but important of the control factor is solid acid and solid base. One raw material is solid acid. One material is a solid base. This means but the most of ceramics is a combination of the acid and base, because Phosphor material is always the alkali metal or alkali earth. Another opposite side is the silica, phosphate, and the vanadate, and the tungstate. This is a good acid. So that easily, for Phosphor material, one of the not good combination is YAG. Yttrium. Yttrium is not so strong. And alumina is not so strong, almost neutrality. Such a case, temperature needs a more high temperature, over 400. 400 to 500. But we use a more higher temperature, we can get the nano size YAG by this technique.
That's big,
yes.
Big advantage.
Thank you. Well, thank you for a very nice lecture and procedure, and thank you for the advice of the kitchen chemistry. My question is, how does the kinetics of the reaction depends on the size of the particles of the reactants?
Raw materials and size is not independent. So if we use a more larger particle, we need a more longer reaction time. But the final product is always the same size, 5 nanometer nanocrystal. So only simple penetration from the water. This is important and kinetic and control factor. So we need a big size one and a single crystal one. So we need a long time. But the reaction temperature is almost the same.
Mm-hmm. Okay, thank you.
Thank you.
Okay, let's thank Dr. Toda's talk again. Okay.
Thank you very much.
Thank you. I will start a second one. It's Dr. Wang Wei Ying from the, let's see, I saw this. Professor? Here. from Hong Kong Polytechnic University. The title is Phosphorescent Soft Salt, Property and Applications. Dr. Wong, okay.
Okay, first of all, thank you, Chairman. And I would like to thank the organizing committee for the kind invitation. So we are still waiting for the PowerPoint. Okay. Okay. Okay, so as we know, phosphorescent material is a very important candidate for many applications, okay, including the OLEDs. And we have spent a lot of time on designing and synthesizing some metal complexes, especially the platinum and iridium heavy metal complex, which can show very strong phosphorescence. But one area that has not been extensively studied is the soft salts, okay, in which actually it contains two metal complexes, which are held by some non-covalent interactions. So in this talk, okay, I will try to share with you some of our recent work in designing these phosphorescent metal salts, soft salts in different areas. And in fact, for these soft salts, okay, as you can see, we have two metal complexes. One is cationic and one is anionic. And you can easily tune the structure of these two metal complexes that can show different colors and also different photophysical properties. And one of the main advantage is that, okay, we can easily control the emission wavelength of these two complexes so that you can easily have two distinct emission spectrum in one single picture. And also, in many cases, okay, there is also energy transfer between the two metal complexes that can also facilitate to design some stimuli responsive materials. Not so sensitive. So, as you know, okay, different metal complexes can show very interesting phosphorescent properties. And these metal complexes actually show very good photostability, long emission lifetime, high quantum yield, and large stroke shift. And finally, we have the tunable emission spectrum that can show, actually that depends on different ligands that we use. What's going on? I don't know. I think it's not sensitive, your computer somehow.
Maybe a little far. You can move to the side.
For phosphorescent compound, okay, they can show different properties and applications, okay, including the OLED, sensors, memories, device, and also bioimaging. But in this design, okay, we are using two different metal complexes. So, for example, we can use it as a pH sensor that can sense different pH values. And in this design, okay, we have introduced this pyridine on the terminal so that it will be sensitive to the proton. And they emit different color. Okay, this is a red and this is a blue emission. But when the pyridine is protonate, then it will actually quench the emission so that the red emission will be gone. And then in that case, you have an energy transfer from the blue to the red color. And we can also prepare the corresponding control compound, which consists of only just one metal ion. Okay, so this A1 and C1 are the model compound for comparison. And from the emission spectrum, you can see, okay, for the blue emission, it consists of well features, okay, emission pattern, which correspond to the triplet pi star ligand center excited states. And for the red emission, basically, it is broad and featureless, so that it corresponds to the MLCT transition. And actually, the emission intensity ratio of the two compounds varies depending on the solution concentration. That means you have a different extent of the energy transfer between the two complexes. And in fact, if you have higher concentration, then the emission will go to the red side. Okay? If at a low concentration, then the emission will be mainly the blue emission. And but as you increase the concentration, then the concentration of the C1, okay, is higher, so that it will actually quench the emission of A1. So you can see from the Stern movement plots, you can measure the quenching rate of this process. As I mentioned, okay, it is pH sensitive for the red emission, okay, because of the presence of the pyridine ring. Then if you don't have a different pH value, then the blue emission is invariant of the pH value. But for the red emission, then it is more sensitive to the pH value. So you can see from this picture, at low pH, then if it is mainly blue in color, at a higher pH value, then it will show a red emission, red color for the complex. And if we are trying to develop the co-stinting experiment, okay, for the two separate A1 and C1, you can see the overlapping ratio is only about 70%. But for the soft salt, okay, the overlapping ratio is much higher, up to 94%. It suggests that, okay, the S1 in the cell is remaining intact, without falling apart from each other. And one of the advantages of using this radiometric sensor is that, okay, we can easily enhance the visibility of the image. So if you look at the blue channel at different pH, okay, the intensity does not change too much. But for the red channel, it changes a lot, okay, depending on the pH values. And so if you take the ratio, then you can get a much clearer and well identified, okay, image. So you will help people to distinguish, okay, between the signals. Another interesting feature is that, okay, this soft salt can show different phosphorescent lifetimes at different pH values. So you can see here, if you move the pH from low value to a high value, then the average emission lifetime actually increases quite significantly. And this is also indicated from the lifetime image. Okay, if you have a different scale, okay, so if you have blue color, that means the average lifetime is much smaller. And if you have a much red color, then the average lifetime is higher. So you can see the variation of the image color in this picture, okay, at different pH values. And then this system can also allow you to detect, okay, the intracellular pH variation based on this PL lifetime difference. And we can plot a calibration curve, okay, over a wide range of pH. Then you can easily measure the pH of an unknown sample based on this intensity ratio. And this can also allow you to study the effect of different redox substance on the intracellular pH variations, okay, as you can see for different conditions here. And then we can also design this soft sort in another system, okay, that can allow you to detect different oxygen concentration. And as you know, for phosphorescent, okay, triple state, then it is more oxygen sensitive. But for the singlet excited state, it is less oxygen sensitive. So in this design, we have two different types of complex. The iridium complex is phosphorescent, and the zinc complex here is fluorescence. So you expect, okay, the difference between the two, okay, in the oxygen sensitivity. And then we can use it to sense different oxygen levels. And these are the photophysical data for this soft sort and also the corresponding model compounds. As you can see here, okay, if you have a high oxygen level, then you have a blue emission basically from the zinc, okay? And if you don't have oxygen, then it will give you the phosphorescence from the iridium, which is which is in the red color region. And if you have different amount of oxygen level, then you can see the variation of the intensity for the emission band. And this also allow you to measure the rate of the quenching between the two complexes in the soft sorts. So like the previous case, okay, if you can run the radiometric imaging, okay, for different oxygen levels, then if you have a higher oxygen level, then you can see the red color, okay, for the red channel, and the low oxygen level, the red color, okay, for the red color, they are different significantly. But for the green one, they are quite similar to each other. So if you take the ratio of the intensity, then you can see a much clearer, okay, variation in the images. And we can also measure the lifetime, okay, do the lifetime imaging. Then we can also give you some idea how the oxygen level is related to the lifetime. So apart from these two systems, we can also build up some system with the platinum, which is mostly square planar in geometry. So we have designed two platinum complex, okay, in this way. And in fact, we can also confirm the structure by X-ray crystallography, showing that you have very close platinum-platinum interactions and also the pi-pi stacking interactions. And these are the photophysical data, okay? Basically, it's a mixture of the two individual metal complexes. And we also try to understand the photostability. So you can see here, as time goes on, the intensity does not drop, okay, too much. And the compound basically is non-cytotoxic, okay, as you can see from the MTT data. And in this case, we also try to do it, okay, in a mouse, okay. So we have this in vivo imaging experiment showing that the dye, okay, in different part of the mouse, okay, show different intensity. Although we did not study in detail how this will be useful in biological system, but at least you can see it has good potential to be studied, okay, in the future based on the properties of this soft sort, okay. And then we can also design this phosphorescent soft sort in some so-called stimuli responsive materials, which is a very hot area in the material science. And for stimuli responsive materials, we can have different types of stimulus. One is so-called electrochromic, okay, that means you have electrical potential. Then you have mechanochromic, that means you have the pressure or force. And then photochromic, okay, we have the use of light. and then we also have the heat, okay, thermochromic. So different stimulus will lead to different photophysical properties variation. So we are trying to design, okay, some complex or soft sort, okay, for this purpose. And usually for metal complex, okay, we will see some non-covalent interactions, which is very important in affecting the properties. And some common examples will be the hydrogen bond, metal-metal interaction, and also the pi-pi interactions. Okay, so in our case, we focus mostly on this, okay, for the platinum, okay. We have metal-metal interactions. So in this work, okay, we are trying to use the excitation wavelength as a stimulus to change the emission color of this platinum-based soft salts. So in this design, we have two platinum complex, okay, one anionic and one cationic. Okay, they are basically square planar, so that we expect, okay, when they are getting close together, then we have a very close interaction between the two complexes. At the extreme case, okay, if you have the pressure, okay, or breathing, so that the molecules, okay, the two complexes are getting close together. In this extreme case, the separation is basically the same. But in the random case, in the random state, then you have different distance between the two metal complexes. So for this original or initial condition, we expect they have different photoexcited states. That means you will have a different energy for the emission. But after you create a sample, and then you bring the molecules together at the same distance, then you have only just one single excited state. So in that case, you will have just one emission wavelength, okay? No matter how you change the excitation wavelength. So in this case, in the random case, we have so-called the excitation wavelength dependent state to be on. And for this case, okay, you don't have any excitation wavelength dependent phenomenon. And we also found that by so-called softened vapor framing process, then you can actually revert this process to give you the initial state. And because of this platinum complex, okay, we have aggregation, so we also look at the photophysical properties. Okay, these are the absorption spectrum, and this is the emission spectrum. So from both, okay, experiment, we can see that if you increase the proportion of the non-solvent water here, then you expect to see the aggregation. So you see a new excited state, so-called metal-metal to ligand charge transfer. And this will lead to a redshift in the emission and absorption maximum. And this aggregation can also be confirmed by following the animal studies. So you can see if you increase the amount of T2O, then the peaks, the animal peaks, will become broader and broader. So it is consistent with the interaction between the molecules, okay, in this aggregate state. So from this experiment, you can see if you have the initial state, if you shine the material with different excitation wavelength, okay, 360, 520, then you have different emission color. And if you take the photo or the spectrum at different wavelength, then you can see they also give you very different emission maximum. And this is the case for the pure sample, and this is in the thin film, okay, after doping with the soft salts. And we also would like to confirm that, okay, it is due to the different excited state, okay, in the sample instead of due to the different nanostructures. So we have tried to look at the mechanism by looking at these nanofiber structures. So we deliberately grow, okay, different fibers of different dimensions. And then we take the XRD and also the emission spectrum. Okay, first of all, for this one, okay, basically the D-spacing are almost the same for different parts of these nanofibers. And then for the emission, okay, it is also found that if you use different excitation wavelength, they will give you just the same emission wavelength. So this is the study that we can obtain. So based on this, okay, we can exclude that it is due to different fiber dimension. And then, in fact, as I pointed out before, we believe it is due to the different platinum-platinum distance in the sample, okay, at different situations. So if you have the initial state, okay, after grading, then you can see that it will give you a redshift in the emission because of the aggregations. But in this off state, if you have different excitation wavelength, then it will give you the same emission maximum. That means the system is off, okay? But if you have this softened vapor filming, then you can revert the situation so that if you have different excitation wavelength, then the emission maximum will be different. And we found that this on-off state can be repeated many times. Okay, so you have framing and breathing, then you can have a cycle. And this is also consistent with the XRD spectrum we obtained for both the initial state and the breathing state. So you can see that after breathing, the crystallinity will be lost. And then after you do the softened vapor framing, then the crystallinity will be restored, which is quite similar to the initial state. So in terms of application, we can use this soft sort, okay, to make the so-called anti-counterfeiting label for security protection. So because only the manufacturer knows, okay, how you design the system. So for example, if you build up the label, okay, with this butterfly, okay, pattern, then if you we know, okay, it is already grid, so it is in the off state. So no matter how you use the difference, okay, in the excitation wavelength, you will get the same color. But if you have the softened vapor filming, then it is in the on state, so that you can see they show different emission color. Okay, if you play the trick, then if you just breathe half of the butterfly pattern, then you will see that half of it will be the same in color, and the other half, then you have different in color. And then finally, if you grid the whole pattern again, then you can get the same situation as here. So we can actually easily design this so-called reversible on-off switching process based on this soft sort, which is useful for security protection. And finally, okay, we would also like to introduce to you another stimulus. Okay, so the previous one is so-called excitation wavelength as the stimulus. And then in this case, you have the electric field. Okay, although we do not work on the soft sort yet, okay, but in this ionic complex, you can see that this electric field will stimulate the self-assembly for this ionic molecule species. So for this platinum complex, okay, again, we expect there will be close platinum-platinum and stacking interactions. And we have the crystal structure obtained for this compound. And after you applying the electric field, you can see that the molecules will be aligned so that it will show you different photophysical properties. So this is the original case, okay, before the application of electric field. Actually, if you construct these nanostructures, then it gives you a nanorock. But after you apply the electric field, then you can see that it actually grow in a nanoribbon. Because we have so many nanoribbon together, then finally it appears to be a cluster. And this is the index, okay, for the elemental analysis of this nanoflower. So you can clearly show that you have all the elements present. So that means this nanoflower actually consists of the original metal complex, but in different nanostructures. And this is the growth process of this nanoflower as time goes on. So you can see at different time iterations, then you have different pictures. So at the end, we have obtained the flower-like structures for these nano materials. So we believe that, okay, this is basically due to the reorganization of the of the molecular arrangements after you apply the electric field. So this is the initial state, okay? So you have alternating layers of the two ions, okay? So it will give rise to these nanorock structures. But after you apply the electric field, then they reorganize so that you have the ribbons, okay, a small ribbon like this. And then if you have many ribbons together, then you will cluster into a flower. One interesting feature is that, okay, both of these nanostructures are very stable under normal conditions, but they show different photophysical properties, including the emission color and also the lifetimes. So we have, for example, in this case, you have the emission spectrum. The rock light structure will give you the green emission, and the flower light structure will give you the more or less orange-red color. And this is also consistent with the image, okay, we obtain. So this is the green one, and this is the orange one. And we also observe that these different nanostructures will give rise to different lifetime, as you can see from this lifetime imaging experiment. So you have the scale. The bluer one will be of lower lifetime values. The red color one will give you the higher lifetime, longer lifetime. So you can see from the image, so it will be more red for the rock-shaped structures, and it will be more blue in color for the flower-like structures. So that means if you apply the electric field, then the lifetime actually will drop, okay, from higher values to the lower values. Okay, so basically you can see how we can use different soft salt structures to design, okay, different stimuli responsive materials depending on the process, okay, or the application you would like to see. So finally, I would like to thank all the people who are involved in this work and the financial support from the Hong Kong government. So this is the end of my talk. Thank you very much for your kind attention.
Thank you, Professor Wang, for a nice presentation. You mentioned for the phosphorescence, you still can do the on and off. I don't know for the phosphorescence, the longevity actually determined by the triplet state, right? So in this case, I don't know how can you turn it off, on and off.
You mean for the excitation wavelength dependent emission spectrum?
Yeah, not okay. If you go back, I think you have the. I forgot which but you say you can turn it on and off. Yeah, maybe.
This one, yeah.
Yeah, right. This is the fluorescence or phosphorescence.
This is for phosphorescence.
Okay, fluorescence. Okay. I think fluorescence is okay. It's reasonable, but for phosphorescence, then you cannot turn it on and off, right? Because that is determined by the triplet state.
Yeah.
Okay, thank you.
Thank you for a very nice talk, very interesting compounds. I have a question about the first part of your presentation on the measurement of pH and oxygen in HeLa cells. Have you investigated the mechanism of intake of these complexes into the HeLa cells?
The intake?
The intake.
Oh, okay.
What kind of mechanism?
We did not study in detail, because we just want to look at the outcome, okay, based on the different pH or different oxygen content to see the change.
Okay.
But it is right, okay, it is important to see how the cell actually take up the material, yeah. But we did not study in detail.
Yeah, especially depending on the structure or on the charge of the complex, it may change. And the localization inside the cells is in the endoplasma?
I think in most cases in the cytoplasm, I think.
Cytoplasm.
I think so.
Yeah. Okay. Thank you very much.
Okay, thank you.
Yeah, because as you know, the development of semiconductor, the first generation is silicon. The energy gap of the silicon is about 1.1 EV. And the second generation is the gallium arsenide indium phosphide. Whose energy gap is about 1.5 EV. And the third generation is gallium nitride, whose energy gap is about 2.2 EV. Now the fourth generation is the metal oxide, whose energy gap is about 3.0 EV. So you can understand the progress of the semiconductor material, the energy gap is increased. Why we need the high energy gap material? Because if you use the high energy gap materials, the resistance of the damage from the radiation is improved. The others, the material fabricate device from the materials, it can be used in high temperature and high voltage, so that it could have the high power and high speed performance. So that the metal oxide is very important for right now in the world, because you can understand if we use some device in the 5G 5G station and charging station, so that the metal oxide material is very important. But there is a very disadvantage, because you use the method to deposit metal oxide, there are a lot of the oxygen vacancy and the defect. The induced oxygen vacancy would be induced electron, so that the material would be the N-type semiconductor naturally. But if we like to fabricate devices, we need the P-type insulator and the N-type, so that it is very difficult to deposit insulated films and the P-type. Because if you like to deposit P-type metal oxide, you should deposit many P-type impurity, so that it's very difficult. So the disadvantage of the metal oxide material has the advantage of the oxygen vacancy. So that how to improve the density of the oxygen vacancy is very important for our research. So that in this talk, this outline, I like to introduction some of the luminous method. And I introduced my design system. The system we call the vapor cooling condensation system. Using this system, we can make to improve the oxygen vacancy in the metal oxide material. And we use this one to make some devices. This is the method for the luminous. We have the fluorines. And this fluorines, that means the material absorption photon, then very quickly to emit the light. The time is shorter than 10 minus 8 seconds. So that we call this material is the fluorines, so that you can find if the photon excited to this level and very quickly to the ground state to emit the light. We call this fluorines. And general, we have this material and the prepare method. And second, we call this the phosphorines. That means the material absorbs the photon, then emit the light slowly. This we call the phosphorines. And the phosphorines and the method is are presented in these comments. And this is, I think that to mention this again. And the third method to make the photo the luminance, we call the electroluminance. That means you using the P-type material and N-type material. You apply the voltage, and the electron hole pair would be the combination to emit light. And this emit light, the wavelength, depending on the energy gap of this material. So that we using the metal oxide to make the electroluminance, because the energy gap is very high, so that the UV wavelength would be emitted by metal oxide. But as I mentioned before, the metal oxide material should have very low oxygen vacancy, so that you can make P-type to fabricate this one. And as you know, you like to make efficient emission of the PN junction. The channel we need to the combination in this interface, so that we should use the insulator here, so that emission light from the insulator there, so that we should have the P-type, N-type, and insulator of the metal oxide material. Because I said before, how to avoid and reduce the oxygen vacancy in the metal oxide, we developed this system we call the vapor cooling condensation system. That means the material would become the vapor material, and we cooling the vapor material and then dense on the substrate. We using, this is our system. And the best idea to design this system, the first we understand if the ion Smith forces the ion by using the heating the ion, heating this one, so that you can heat the ion at a very high temperature, then treat the material. After this, he quenches the water very quickly, so that you will the material was heated at a very high temperature and quenched in the very low temperature. The material property would be improved. This is one basic idea we use this one. The second, you can understand in the ME system or high vacuum system, he like to grow very high performance films. You can find in the ME system, they put the material in this crucible and heat this one, and put the substrate here so that it can be gold on this one. But you can understand the chamber will be cooled by liquid. Why they using the liquid nitrogen to cool the chamber? Because you emit some material over here would be deposited on the chamber. If you don't to cool the wall, the material would be emitted from this core, so that would damage the material you deposit. So that you like to avoid the emitted, you should cool the material, so that in this system we can find the inside of the chamber. You can find this is some crucible, so that the material you like to deposit, you can put the powder on the tungsten crucible. If you heat the crucible, the material would be vapor material would come from this material and this one, and we put the substrate here so that it would be deposited on the substrate. Because we're using the liquid nitrogen to cool the holder, so that the material would be deposited on the liquid nitrogen cooled substrate. Then the vapor first will quickly to cool, like the punch in the water. The second, because this is very low temperature, so the deposited metal oxide would be not emit the oxygen, so that we can improve and decrease the oxygen vacancy. This is the basic idea we do this one. So that you like to deposit metal oxide, what's the material you just put here, and you like to deposit of the metal oxide, the impurity powder also put here. For example, you like to go on the gallium oxide, and you like to dope in HF so that you can heat both of these materials, so you can get. The others, you can control the doping concentration. The first, you can control the temperature of this doping material. The other method, you can put more material here, impure material here. Because the more surface, you can get more vapor materials. This is our designed system. And we using this material, this system to deposit, because I said before, we can using the liquid nitrogen to cool the substrate, and we measure if you don't use the liquid nitrogen to cool the substrate, for example, you can deposit the zinc oxide. You can find the short emission is the material itself, but in the visible band, you can find a lot of the PL emission, because this visible light come from the oxygen vacancy, so that we can find you don't use the liquid nitrogen to cool the substrate. There are a lot of oxygen vacancy. But if we using the liquid nitrogen to cool, you can find the density, the intensity of the visible band is very low, so that we can you can understand that we can make very low if we can work. So that, for example, for the gallium oxide, you can find the deposit of gallium oxide is amorphous, but you can change the structure of the crystallize of the gallium oxide. You can using the post-annealing process, so that you annealing process more, you can get a polycrystal. And you like to, this is the, you using the silicon to deposit, to dope it into the gallium oxide, different silicon content, we can get a different performance. So that, as I said before, it is very difficult to get the P-type metal oxide. So at first, we using this structure. This is grown by the MOCVD system, and we using our system to deposit the gallium oxide here, and using the same system to go on the silicon dope gallium oxide. And we make this as the PIN structures, and this is the LED structures. So that this is the IV curve we can find, and you can find we using the different injection current. We can find we can get the UV emission LED. The most important, you can find the visible band, the intensity is very low. That means we can get very good performance of the gallium oxide. Okay, as I mentioned before, it is very difficult to get the P-type, so that we're using the spatter to deposit the nickel oxide as the P-type films, so that we can using this one. We're using the sapphire substrate and go on the N-type gallium oxide and insulated gallium oxide, and using the P-type nickel oxide. We also get this P-type as the PIN LED structures. And this is a band structure. Because you use the nickel oxide, we have the heat junction between the nickel oxide and the gallium oxide. Because heterojunction would improve the LED performance. And, and you can find we also using different injection current. We can get the UVC, it's a very deep UV emission. The others, this is the PIN structures, and we know if we the insulator region we using the multiple quantum well, the performance would be improved, so that we using the gallium oxide, aluminum, gallium oxide as multiple quantum well. We using the different period of the multi-quantum well. And this is the band gap of the multi-quantum well. And we can find, if we just using the PIN structure, the emission is the break, and you using the multi-quantum well, the period would be improve the performance. So that I introduced my design system to deposit, and this is a very simple system, and this is a very simple method to improve the disadvantage of metal oxide. Thank you.
Any questions? Okay. I got a question. You got a lot of DUV LEDs. What is the efficiencies?
The efficiency is low because it is just amorphous, not a single crystal. So, but we demonstrate that our system can improve, can deposit very low oxygen vacancy. But most of these, our device use is the photo detector. Yeah, but because this conference is about luminance, so I don't to present the photo detector. But you fabricate the photo detector UV, you can find the gallium oxide. We can dope different material. The energy gap is changed, so that the UVC, UVB, UVA, very band UV we can detect. So the most important, I believe, that used for the photo detector, because using this deposit, the cost is very low.
Maybe the same issue is hard to get a P-type.
Yeah, because the insulator we can get, right?
Yeah.
So that you dope in the P-type. It's just you don't need a lot of the P-type material as the impurity, because what's the mean of P-type? Because the whole concentration is larger than the electron that we call the P-type. But if you don't reduce the oxygen vacancy, because a lot of electron exists, so that you need a lot of the P-type impurity. And maybe 14 years ago, we using this system to deposit the zinc oxide. The concentration would be lower than 10-15. That's the time this is the first record in the world. Yeah, because we using the two very basic idea. And that's basically, everybody knows this one. And this system, the original is the thermal coater. Thermal coater is very, very cheap. And we just modify the top, and we using the liquid nitrogen to cool the whole. And because the people who study the films, they have the one common idea. You like to deposit high performance thin film. The substrate should be heat to 300 or 400 degrees. Why they need to heat the substrate? Because the deposited material should migration to improve the performance. To improve. Now, why we using this low temperature? We also can get high performance films because we published the mechanism in 2010 in the JAP, Journal of Physics, because we find the migration energy of the metal oxide is lower than the silicon dioxide and other, so we can migration that one. Yeah.
The signal is very much like an initial stage of the blue LEDs. It's very nice to see this. Okay.
Yes, thank you to come to this conference, give us such a nice talk. So you give us the results on the gallium oxide. So as far as we know, the next generation will based on the silicon carbide. So do you have any comments to extend the gallium oxide to silicon carbide for your studies? Thank you.
Because if you like to fabricate the material, that's you should to have very quick, what's the coefficient? That's you like to, you work in the high temperature, you should to reduce the temperature, okay? So that thermal coefficient of that, because the silicon carbide is much higher than the gallium oxide. So the silicon carbide is always using the electron devices as the substrate or the device. But the silicon carbide is very expensive, and you cannot get a good large size of the substrate. So that, as I mentioned, you like to get a very high performance device, you should use a single crystal. But the single crystal should use MOCVD or MB, and the very expensive to grow that one. So that for the sputter system or the other systems like our systems, we cannot get the single crystal, but it is very cheap. So that for the application, you should to using the expensive system or cheap system. That's for the application.
Thank you. Okay, thank you, Dr. Lee, and all our three speakers in this session, and thank you all for attending this session. Okay, I think we can enjoy the coffee break. Thank you all.
Unrelenting activity and combined history of its players. Pursuing lives of adventure, warfare, and prosperity, they share this existence in the biggest single shard, free-to-play MMO of all time.
Okay. Good morning, everyone. This is second session. Second session. So we have three invite keynote speaker, but unfortunately they will give a presentation on June 9, June presentation. So first speaker, let me introduce, is Dr. Takahashi Seto. His title is Unique Large Stock Shift Unrelated to Refractive Effect for Crystal Field Splittings.
Thank you, Chairman. I'm Takatoshi Seto. First of all, I express my thankfulness to the organizer and the committee for a great and considerable arrangement of this international conference. Under the special circumstances, my information was not able to be exhibited in the conference book. Here, a part of information of mine. Here, I am former research advisor, Japanese. My background of education and experience is physical chemistry and recent 25 years emitting materials. Here, I will talk concerning review related to me, made by me, Japanese. A unique large stock shift and our finding shrink of large stock shift. Application is LED lighting and plant growth. Previously, Daicho et al. Found potassium calcium phosphate fluoride, which has a large stock shift near UV excited deep red emission. We found the unusual phenomenon, much shrink of stock shift under the substitution of special cation. Only rubidium induced the tremendous shrink of the large stock shift. Wavelengths of near UV excitation is not much changed, while emission wavelength is much depressed from deep red to yellow to green, finally to blue-green. Substitution of rubidium improved thermal stability. These phenomena are due to the shifting and losing of excitation state curve toward larger European bond distance on configurational coordinate. The distance between the bottom of excitation state curve and the ground state curve is minimum in case of a double potassium sample, providing the shortest energy emission, deep red. The distance is medium value in case of rubidium potassium sample, providing the medium energy emission, yellow. The distance is maximum in case of double rubidium sample, providing the largest energy emission, blue-green. This shifting increases the barrier between the bottom of excitation and the crossing point of the excitation state and the ground state. This is activation energy for electrons jump over the crossing point to non-emissive process. So rubidium induces this shifting and increases the activation energy, improving thermal stability. Further, we have added new cation to this rubidium potassium phosphate fluoride. Magnesium effect for increasing emission intensity was found. However, sodium or magnesium or cesium never changed the stock shift. Only rubidium changed the stock shift and emission color. Magnesium increased not only emission intensity, but also decay time. This is due to the depression of non-emissive process by magnesium. we fabricated near-EV LED device, including this magnesium rubidium yellow phosphor and the famous BAM blue phosphor. Increase of electric current up to 150 milliampere did not cause emission saturation. Color rendering RA was high, 92.3. Good white LED candidate was obtained. Magnesium improved thermal stability, 10%. 90% was obtained at 150 centigrade. Generally speaking, one of the mechanisms for thermal stability is structural rigidity around the europium. Debye temperature can often indicate the rigidity. Debye temperature is increased when atomic displacement parameter decreases. Displacement parameter at the calcium-magnesium site and the potassium-rubidium site were much decreased after magnesium's substitution. Magnesium decreased atomic displacement can help the improvement of thermal stability. Daichou et al. Found calcium strontium silicate chloride near UV excited yellow phosphor. We found that substitution of smaller cation magnesium shrunk the Stokes shift, and the substitution of larger cation barium much increased Stokes shift. Then we found near UV excited red emitting phosphor barium SSC. We fabricated LED device, including this red emitting barium SSC and the famous blue emitting BAM. Yellow CSSC and BAM provided color rendering RA 80.4, while our new barium SSC and BAM provided RA 90.5. Much improving color rendering. Difference between CSSC and the barium SSC is lattice vibration. Raman shift of SIO shows this difference vibration of SIO gets weaker due to the elongation of SIO weakened vibration constant, which is shown in the figure and the table. So large barium substitution expands the lattice, elongating bond length, then weakening the vibration energy. We observed temperature dependency of emission width is quite different between CSSC and barium SSC. As is shown in the middle figure, the inclination of emission intensity against the temperature is 24% in CSSC and only 15% in barium SSC. Henderson-Imbush equation concerning half width of emission is the function of Huon-Rees factor and phonon energy. According to the fitting, Huon-Rees factor is much smaller, 7.3 in barium SSC than CSSC, 13.1. We investigated local structure where barium SSC's local structure is much expanded compared with CSSC. The former's average bond distance is 2.75 angstrom in barium SSC and 2.66 angstrom in CSSC. Brilliant experts have considered so far large Stokes shift is due to reorientation of europium anion configuration at excitation in case of the and symmetric coordination of anions in ground state. Here we observed europium anion and symmetric bond can be stretched by the substitution of larger cation barium for the lattice. During excitation, europium gaining higher energy can move to more stable Lewisian space, that is, tremendous reorientation due to the longer bond lengths and larger space. Due to the longer bond distance, the lattice phonon cannot easily transfer, so phonon influence is weakened to europium, and the electron-phonon coupling of europium is getting smaller. We observed tremendous large Stokes shift, where larger barium elongates and symmetric europium bonds. Then Huon Rees factor gets smaller, which is reasonably opposite to the conventional idea. The equation based on Henderson-Imbush theory, Stokes shift equal to 2s h or 2s minus 1 h omega doesn't work in such large Stokes shift. Probably because the Lewisian excitation state curve is never equal to the ground state curve in large Stokes shift. Expansion of unsymmetric europium bonds causes further larger Stokes shift because excited europium can easily move towards more stable large space during excitation on configurational coordinate. Here we observed double Stokes shift, larger and smaller. Strontium calcium phosphate received sodium substitution. Then larger Stokes shift from near UV excitation to red emission, while shallow blue does not change. Again, we watched unsymmetric europium bonds providing large Stokes shift and symmetric europium bonds providing quite a small Stokes shift. Again, we have considered that asymmetric local structure is likely to induce large Stokes shift and broad emission. Returning to rubidium's effect on potassium calcium phosphate fluoride, we investigated why much shrink of Stokes shift happens from deep red to blue-green. The above mechanism is different from that of my previously finding industrial LED phosphor, LSN or LCSN, where nephrozetic effect and crystal field splitting elongate not only emission wavelengths, but also excitation wavelengths. In the original potassium sample, during excitation, O1 EU CaO2 angle can be expanded, helped by the rotation of nearby PO1 bond of PO4 tetrahedron. Based on the paper of Daicho et al., we watched that in case of rubidium substituted sample, this O1 EU CaO2 angle in the ground state is shrunk from 97 degree to 91 degree, and nearby PO1 bond is much shrunk from 1.577 angstrom to 1.47 angstrom, probably depressed by nearby bigger rubidium. Therefore, in case of rubidium sample, during excitation, O1 EU O2 angle cannot be expanded, depressing long relaxation of europium on configurational coordinate. When this mechanism is true, we got the next idea. If high pressure depresses the expansion of this O1 EU O2 angle, we would be able to obtain tremendous shrink of large Stokes shift. Then we tried to use diamond anvil cell, including powders of potassium sample. We surprisingly observed that with increasing pressure, emission wavelength significantly decreases from deep red to yellow to green, finally to blue-green. In case of rubidium sample, under the increase of pressure, almost no change, and a little increase probably due to the small increase of crystal field splitting and the nephrotic effect induced by lattice shrink. In case of rubidium potassium sample, emission wavelengths decreased from deep yellow to green in the region of 0 to 5 gigapascal, then started increasing from green to yellow in the region of 5 gigapascal. This case has both increase and decrease of emission wavelengths, including a new mechanism and crystal field splitting nephrotic effect mechanism. We investigated in situ Raman spectra under high pressure. Generally speaking, with increasing pressure, 4 kinds of vibration of PO4 tetrahedron, that is, new 1, PO asymmetric stretching, new 2, OPO double degenerate bending, new 3, PO asymmetric stretching, new 4, OPO triple degenerate bending, little shifting to higher energy. This is due to shrink of lattice and PO4 tetrahedron under pressure. Surprisingly, we found that in case of a potassium sample, with increasing pressure, the new 4 OPO triple degenerate bending gradually decreases and finally disappears over 14 gigapascal, which coincides with much shrink of Stokes shift. Moreover, in case of rubidium sample, from the starting point, 0 gigapascal normal pressure, new 4 disappears, which coincides with much small Stokes shift of rubidium sample. From such a coincidence between the shrink of the Stokes shift and the depression of OPO bending of PO4 tetrahedron, we concluded the next new mechanism. In rubidium sample, much shrink of Stokes shift is due to non-rotation of PO1 depressed expansion of O1 EU O2 angle, which is caused by nearby larger cation, rubidium. Under the high pressure on potassium sample, much shrink of Stokes shift is the same reason, due to the quenching of PO1 rotation depressed expansion of O1 EU O2 angle, which is caused by the shrink of lattice and PO4 tetrahedron. We reminded the next phenomena, including a new phenomenon. First, large Stokes shift happens in unsymmetric bonds around the europium, because at the excitation, high energy europium anion bond can move to place of stable and large space. Second, in case of expansion of such unsymmetrical local structure around the European, further larger stock shift happens, while in case of a shrink of local structure, stock shift can shrink. Third, large stock shift is likely to be accompanied by less phonon dependency of emission, such as smaller Huon-Reis factor due to large bond distance around the European. We noticed that the new phenomenon, much shrink of stock shift, has quite large shift for increasing pressure. Present pressure sensor is Ruby, which has a 0.365 sensitivity, while our pressure-induced shift of emission wavelengths for potassium sample is much largest ever, 14.3 sensitivity, which is 40 times for conventional Ruby. Therefore, our finding has a possibility of application to the highest response sensor for measuring pressure. I have already talked the application of large stock shift to LED lighting. Finally, I will talk the application plant growth. Our plant growth is a sunlight converter, transferring near UV or blue of sunlight to the deep red, which is important for accelerating crops growth. Our sunlight converter is completely different from the conventional Farber-Lof's greenhouse type. We have tried our rubidium phosphor fluoride or double stock shift sodium phosphate for chlorella growth. The result was positive, plus 12% and plus 28% increase for chlorella growth, respectively. The next is growth of lettuce and important tomato series. We applied our new type, manganese 4 plus strontium aluminate, to plant growth. By giving our new technology, the external contaminant efficiency of this manganese 4 plus phosphor increased to 54%. From 5 samples, lettuce growth was accelerated plus 40%. From many 15 samples, the growth of important mini tomato fruit was accelerated plus 49%. Tomato growth under the conventional emitting greenhouse was maximally plus 20% in the world. So our result, plus 49% increase, is surprising. My talk is finished. Thank you very much for your attention.
Is it online? Yeah. Okay. This is a question, open question time. Do you have any question to the speaker?
Oh, okay. Thank you for a nice presentation. I have a question regarding use the luminescence materials to enhance the plant growth. We know this concept has been proposed like 50 years ago, but for actual applications, there's some challenges. For example, how long the material can be used. Okay, generally speaking, for the farmers, they need the material to be used for like up to 5 years. So do you think your material can be used in the greenhouse for 5 years? You understand my question, right?
Almost. Yes. Professor, thank you very much. So, as you said, for the growth of the plant, the working lifetime is quite important. So, we are using. I am originated from the LED phosphor, maybe more than 20 years. So the working lifetime is quite important. So our using phosphors can have the durability for the working lifetime more than 10 years. So no problem, never problem for the 5 years usage of the, for example, greenhouse. We don't use a greenhouse type, but yes, sunlight utilization plant growth. Yes, so no problem in our case.
Okay,
so
you.
We have partly part of our phosphor, our new phosphor has already been checked for the working lifetime. So no problem. Yes, thank you very much.
Thank you.
It's nice to see your face, Professor Sato. It would have been even better if you would have been here in person, because we really miss you and other participants. My question concerns the pressure sensing. You show that for European 2+, you have a very large shift, 40 nanometers per gigapascal, much larger than for Ruby. I think that's 0.4 nanometers per gigapascal. And that's nice, high sensitivity. But is the accuracy also better? Because determining the position of a sharp emission line, like you have for Ruby, or a broad band for Europium, it's much more precise to determine it for Ruby. So is your accuracy also better for pressure sensing?
Yes. Professor Anders, thank you very much for useful, nice questions. So yes, Ruby has very sharp line emission, and then so maybe it can be accurate for measuring the pressure. So on the other hand, European 2+ phosphorus. Previously, I have presented in the paper, so maybe nitride phosphor. This is also shifting. But yes, as Professor Andrews said, yes, we have noticed broad emission. So therefore, if it is possible, I am considering that one of the peak position of the emission is the most important. Maybe secondly, that even in the case of the broad emission peak, so if we can take the average, so from the integrated intensity of the emission at each wavelength, we can evaluate the average wavelength of the broad peak, broad emission peak. So in this case, we have checked. So as you suggested, so our system is very great. However, the broad emission, sometimes 2 or 3 peaks are included. However, if we take the average wavelength of the such broad emission, so we watched the pressure is here, and then the average wavelength of the peak. Mm-hmm. So very nicely linear. So if it is possible, it can be, I'm not sure so much, but maybe for the next near future generation, so maybe if this way of the usage for censoring is also maybe has a little possibility, I think. The best, yes, I know. The best sensor is the sharp emission. The secondary, if we can take the average. So very nice linear. So in the case of the crystal field splitting increase, conventional one here, but in our case, the opposite. So here, yes. This is very linear. So thank you very much.
Yeah, and thank you for the very nice presentation.
So any other question to the speaker? Okay, so we don't have any questions. So let's move to the next speaker. Let's thanks to the
Thank you.
Dr. Seto.
Thank you, Chairman. Thank you, Chairman. 谢谢.
Okay, in this session, second speaker is Ring Dong Sun, Professor Ring Song Dong. Okay. Yeah, okay. So some little delay. Sorry. So her title is a low threshold concentrated lanthanide converter. So we have some little delay to the system. So wait a moment. Actually, we have a 3 speaker, but unfortunately, the final speaker is canceled, his speaker. So we will have some early lunch time. So that is very happy to us. Are you ready, Professor Sun? And please turn on the speaker. Oh, okay. So please, Professor Sun, please turn on your mic. So we cannot control your mic in here. And the video, please. We want to see you. Can you hear me, Professor Sun? Please turn on the video and turn on the mic, please. Okay. So wait a second. What about 10-minute break?
5 minute break.
Yeah, 5 minute break. Okay, let's have a 5 minute break and then let's start again this session. Okay.
你先把 PPT 把它投影播放。先把它播放。右下角第一个那一个。不是右边。在手里，对，按那个，对，但是它好像不会播放。那你换页会动吗？你换页会动吗？你现在换到。 sorry everybody, is the Professor Sun's she now is already reopened her computer again. So wait a moment. Okay. She's the last one, the morning last one, speaker. Okay.
老师，我重启，现在有声音了。Hello，林老师，我听不到您的声音。
孙老师。
啊，林老师啊，现在可以看到屏幕吗？
有声音。
翻页
那个孙老师，可以请你把那个镜头打开吗？微信，我用微信。你可以开小声一点，因为你那边声音够清楚。然后
现在用的微信啊。
对，用微信的镜头，我现在帮你转到微信的镜头。
微信的镜头。
手机，用手机，不是电脑，用你的手机。
是吧？可是。
用视讯通讯嘛。
那我们的挂断，然后
我挂断再打一次给你，用视讯。好。
好的。
好，拜拜。
拜拜。I don't know。
我们要看到你，不是看你的电脑。你看到我们吗
？I can see part of the conference room.
Okay.
Yeah.
Okay.
So I'm not sure if the slides work.
苏老师，你的喇叭可以关小声一点，就是你会有回音。
Let me see how to. Okay. I'll close my speakers. It's okay.
还是太大声。是不是要把笔电的声音关掉？你直接把你的笔电的那个把它关静音，因为你现在是用手机收音，因为它同时开，所以会有 echo。
So it's okay. It's okay.
你的电脑的那个喇叭有关掉吗
Now it's closed. Let's shut down all of the microphone of my speaker of my laptop. It's okay.
Yeah, it's okay.
So how does it work? How about my slides?
可以，你听得到我们声音吗？
Okay, I can hear your voices.
Okay, so
okay. I can start now.
Okay, but please try against your slide. Can move to second page.
I have moved to the next pages. Okay. It's okay.
Okay, you need to touch the lift the small image second page. 你直接按左边的小视窗，这是你的投影片，直接让它跑到第2页，变成说你要。
我现在已经在翻页，还不动是吗？
哦，你要结束播放，因为你现在是在播放状态下，你先把它关掉，就是变成用一般的这个投影片的状态就好了。
OK。
好。
It's OK。现在可以吗？
然后点左边的第2页，小视窗的那个可以了，可以，现在已经在第2页。OK。
I really cannot understand what happened.
Okay, so now I give the time for the chairman.
Okay, it's a long waiting. Well, anyway, so let me introduce again. This next speaker is Ring Dong-sun. It's a Peking University. So, are you ready? And please start.
Yeah, I'm ready. I'm really sorry. I was waiting for a great expectation to visit this safari in Taiwan, but unfortunately I cannot catch up the conference, so I have to attend it online. So many problems. It's a really hard journey for me. Today, I will talk a little about our low threshold, highly concentrated frequency upconverters. I'm Ling Dong-sun from Peking University in China. Okay. Similar to a few talks in our Phosphor Safari this time, I'm working on lens-night. Most of my research on lens-night nanoparticles and lens-night luminescent materials. And until the last century, at the end of last century, I moved to some nano-sized material studies for example, quantum dots and some doped zinc sulfide, and also the lens-night nanoparticles. For the lens-night, we usually dope different kinds of ions into the host, and then we can have their specific emission, for example, located in the visible or near infrared. It's very unique. So they have a wide application, not only for phosphors, but also for some fainting, and it is comparable, sometimes comparable to commercial dyes and quantum dots. So the first thing I encountered when I entered Peking University, we want to have a very good nanoparticle. So I tried a few strategies or methods, for example, hydrothermal and solvothermal, But at the beginning of this century, we can buy some chemicals from the other countries. So in this case, we can try to do some thing similar to quantum dots. So in our group, Professor Zhang and our students and our colleagues developed a method to synthesize scale nanoparticles of lensnite, different composition, different structure. So in this case, we can have well-defined nanostructure to study their properties, especially the luminescence properties. For example, here, we can see some nanoparticle. We can get the core and the co-shell nanoparticle. We can control the size and the thickness of the shell and the assembly of the different kinds of composition. And we can also get combined with different kinds of luminescence. So in this case, if we came back, what we have done, we think there's also still a lot of things that we should do about the lensnite nanoparticles, especially very active work in the upconversion luminescence studies. So if we find some canyon work, we can find this lensnite nanoparticles have been studied as multiplexing in wavelengths and in lifetimes, and they can use different combination, and also they have showed a great potential as displays and information storage. And they're still going on a lot of fantastic things, still it's attractive and still it's working on. Okay, but for the lensnites, especially for the upconversion luminescence, and not like the commercial traditional phosphors, we have a host to the lensnite and transfer can flourish the luminescence. But for the upconversion, generally it happened between two ions. One is responsible for absorption. They have a relatively large cross section of absorption. And the other one is responsible for, they have a similar or very good energy levels that can accept these energies for energy transfer. For this case, although we can use the near infrared to get very good visible luminescence from the upconversion, or sometimes maybe near infrared, but actually the absorption cross-section is very lower, and the FF transition of the lensnites also hindered the application or the further studies of this kind of upconversion nanoparticles or luminescence. So in this case, we think there's still a lot of challenges in this work. For example, how to get very small and bright nanoparticles, or how to do different kinds of combination for wavelengths or excitation or lifetimes, and maybe even for the polarizations. Okay, so today I will start from our beginning of how to get good nanoparticles at first. And from the literatures, Frank Weigel have reported that for 13 nanometer lensnite upconversion nanoparticles, the quantum yield is quite lower, it's less than 1%. It is cited in a little higher excitation pore density. But we think maybe we can have some ideas on this. Similar to the quantum dots, people are using the core shell structure. For example, Professor Xiaogang also used the core shell to protect the luminescence centers located the surface or near the surface for the pinching from the unsaturated or surface environments. We also can think back of the FF transition of lensnites, because it is parietal forbidden. If we broke the symmetry, maybe even lower local symmetry can be helpful for this kind of thing. And how to do that? We can find some examples of a core shell structure, and also some thing about broken symmetry. Okay, The first example is we use the core shell structure. The core is quite popular. We have sodium yttrium fluoride or different kinds of sodium lanthanide fluorides at the core, and we can select different kinds of shell. Generally, the similar composition of the shell can protect the nanoparticle, but we think if we further taking inside of the application, especially for bioimaging, maybe we should think of something about which kind of shell is benign or biocompatible. So we think maybe calcium fluoride can be used or can be think as a kind of alternatives. So we tried for this calcium fluoride, and we get very good nanoparticle. We can see from the contrast of core and the shell because calcium is a little lighter than the lanthanides. So in the case, the luminescence is greatly enhanced. But people also think, oh, you choose a very not bright nanoparticle because it's a cubic phase. They have a similar space group and similar lattice parameter is okay, for you can get co-shell structure. And how about the hexagonal? They have they think this is the best upconversion nanoparticle for host. So we think of the hexagonal one. And we also try to how to coating a calcium fluoride in this kind of nanoparticle. For example, at first the nanoparticle is spherical, and when they coating the shell of calcium fluoride, okay, we can take a look of the PAM image. We can find very cubic-like structure. So we think this should be something correlated with calcium fluoride. And we, if we take the STEM image, we can see also the contrast from the core and the shell. We are sure that is a core shell structure of our hexagonal and cubic lanthanide and the calcium fluoride particles. Okay, in this case, the luminescence is actually also greatly enhanced. Maybe it is about 1 or 2 orders or even higher. If we compare of our calcium fluoride with the popular used lanthanide fluoride as a shell, we can see from in the similar kind of attachments, the quantum yield is still higher. So what's the reason that behind of that? I think the core and shell, there's people also use of the alloys to get maybe different kinds of combination or some kind of alloy nanostructures. But if you think of the core and the shell, something should happen at the interface. It should also be alloyed. So in this case, if there's similar structure or similar composition of the lanthanide fluoride, this kind of alloy will be happen that the ion diffusion will be happen across the interface. So in this case, if you have different, for example, the sensitive is here and the sensitizer here. If you anneal the nanoparticle, you can find the luminescence will be increased because the submergent ions will be diffused across the interface, and the part of them is still alloyed for this kind of erbium. You can see the luminescence is increased. But for our, calcium fluoride, I don't know why it's not cannot. Okay. For our calcium fluoride as the shell, if you doped different parts into, for example, erbium here and erbium here, this kind of diffusion will not be happening seriously. So if you heat it for a long time, even longer, you cannot see any increase of the luminescence. So we think that this kind of co-shell structure, and especially the calcium fluoride cell, is a good choice, not only for protecting the luminescence, but also for for example, you see here the leakage of ions, and it's also for bell applications. I'm sorry. Okay. And this kind of nanoparticle also is good for bell imaging studies. Because I have taken a lot of time, I will omit this part maybe because it's published. Okay. And with this kind of core shell strategy, we can combine the different parts of the landslides in the core and then maybe different layers of the shell. Not only protect the luminescence, but also the transfer can be controlled in a specific area or specific region of the nanoparticle. So, for example, here you can see maybe a different kinds of or a few layers of the shell. They're responsible for different kinds of luminescence or excitation combined together. It's a very complex structure, maybe you can see. But this structure can be excited in different wavelengths to get different emissions. And if we combine with the liquid crystal, because liquid crystal can be tuned under the electric field, and also we can tune it with the light, infrared light. In this case, maybe you can take the chiral properties of a chiral luminescence of nanoparticles. Okay. So we summarize our studies, and you can see we can find the different strategies for different kinds of doping and core shell structure, and maybe forming some of the vacancies, tune, or you can select different transitions and also increase some parts of the emission. Let's move to my second part of the talk. Another example is about nano lasing studies performance. For lasing, we know is quite famous that we should have a popular inversion that is some of the excited states are populated, or most parts of the excited states are populated. In this case, this excited states can be highly populated in the ground state. So we think we call it population inversion. So in the case, if you shine light or excited this energy levels, then much of the photons or a lot of photons will be emitted simultaneously. And all of the photons will be correlated. They have the same wavelength, they have the same phase, and they have same wavelengths. And the gain medium is most important. But the other most important thing that we should have a cavity to enhance or to realize this process, that the highly populated sites can be simultaneously respond to their ground state. So we have to have a fibro pore or some kind of cavity to select different wavelengths of the light, and also make this kind of a stimulated emission. And this have been actually predicted by Einstein previously. But how to realize, the last century and 60s, it have realized in the Ruby, but how to realize this in nanoparticles, nanosize particles. And from the previous works, semiconductors have been worked as this kind of nanolasers. The semiconductors have a long one-dimensional structure, and they have two ends, this very good fibroporal cavity. But actually, we can construct different kinds of cavity. For example, DBR is very effective. Yeah, we have tried it, it's very effective, but I will not talk about this part today. Another kind of thing is maybe we have macro nanoparticles or macroparticles. the two ends can be used as a fibropore cavity. And also the visible Galois mode is a silica sphere or polymer sphere. The light will transferred and can be totally reflected. In this case, it's similar to the fibrocal cavity, and the light will be amplified in this case. If we think of the difference of the stimulated emission and our spontaneous emission before, they have a very sharp lines. You can see here, very sharp. Maybe if it's a good cavity, maybe it's even sharper than 1 nanometer or 0.1 nanometer. And the other thing is, other character is they have a threshold that it be at a specific excitation pore density, and it is also is polarized. The laser must be polarized. Okay, so what kind of a cavity we should be attract? This is temple heaven. Maybe some of our colleagues, our friends have been there. If someone is whispering here, and the friends can hear your voice here. You say, I miss you so much. I want to attend this Phosphor Safari. If you call here, I will be hear your voice is here. Okay, and this is a kind of a visible gallery. So a kind of a echo wall. For some kind of silica or polymer spheres, it's also can be act as kind of visible gallery mode. For example, here you can see the light will travel inside the sphere, and they will be amplified. We have tried a lot. We have tried actually a long time, but we do not have very good progress. But a few years ago, Emery Zhang and Cohen and James Zhang, and they have published this kind of idea, use this kind of a gallery modes, and they have a very they can be excited in the continuous wavelengths, and they have a very low threshold compared with other kind of a strategy. I will talk about what I have tried a few years ago. We want to assemble our nanoparticles as the kind of sphere one, and we're excited. But unfortunately, we only get spontaneous emission. Even the increase of excitation pore density is higher than a few hundreds of kilowatts per centimeter. But recently, we try to assemble the nanoparticles even more perfect or good than before. We can excite the spherical one. With all of the composed nanoparticle not assemble only assemble the nanoparticle on the surface. The sphere is composed of millions of nanoparticles inside this one. We can take the spectra. We can find some fingerprint of the lasing modes, and the spectral lines is less than 1 nanometer. Actually, similar to the previous literatures, we also use polymer spheres, for example, polystyrene. We coated our nanoparticle on the surface, and it can be realized on different wavelengths of the population version actually. So in this case, we can get the spectra, and we can get the threshold as quite lower for this case. And the luminescence you can see here is very narrow, and it can be down to 1 nanometer, as like the 4.5 maximum is lower than 1 nanometer. And the fluorescence, the emission is polarized, nearly linearly polarized. So we can show this is lasing, upconversion lasing, can be excited in the continuous wavelengths at room temperature, and different kind of upconversion nanoparticles can be combined with this kind of visible gallery mode, and they all can be detected with lasing behavior. And if you combine different kind of nanoparticle together in the same sphere, different wavelengths emission can be is a kind of a white lasing behavior. And if we change a little about the polystyrene, for example, we doped some dyes inside. Actually, we do not change the threshold and also the line-wise. Okay. Yeah. And how about the stability of this kind of upconversion macro lasing? If we shine our excitation, because it's a little higher power density, if we shine light longer, it shift a little, and maybe it's comes from the shrinking because of the polymer is a little shrinking the polymer spheres. And we also test the temperature stability. This kind of nanolasing has a quite higher sensitivity with the temperature. We can use maybe filter in as a kind of sensing studies. Okay, and all of our previous upconversion lasing actually comes from multiple wavelengths actually. But how to get a single mode? Because if we want to use the sensing, the single mode is the best choice. We can take the single lasing modes with is shifting with temperature surroundings or different kinds of attachments. So if we take back of the theory, actually the free space wavelengths traveling in this kind of a cavity can be taken as this formula. Maybe you cannot take it clearly, but it tells that if you shrinking the cavity size, the FSR will be enlarged quite a lot. So in this case, we can shrinking the cavity size. So using smaller cavity, maybe we can get the single mode emission. Okay. We use, for example, 20 micrometer and 5 micrometer and 3 micrometer size, even 2 micrometer size cavity. We can get, for example, here, the single mode in the end. Okay. And another strategy to get a single mode is coupling two sphere together. In this case, we can also use one sphere as a kind of a wavelength filter. You can also get a single mode lasing. Okay. Okay. In the last, I will try to have a little maybe opportunity in the future. With the photon avalanche is quite active in these few years. Photon avalanche upconversion emission can also be combined with our gallium mode to get the this kind of photon avalanche emission upconversion emission lasing. For example, we can get the lasing here near 800, and we take the other kinds of lens size where we have got some of the near-infrared lasing here, but still working on this part. So the problem is, the question is, which kind of a size of the cavity is the best? Okay. For example, here is the near-infrared lasing. Okay, I will, for my conclusion, I'm sorry I'm taking longer time. The thin co-shell structure is a good platform for nanophotonic studies. And within, beyond the upconversion emission, low threshold lasing is very, and should be a good topic in the future. Or I want to maybe if you have any ideas or suggestions, please let me know. And with those things, a lot of room, plenty of room for upconversion emissions. But the problem, the challenging is still existed, is how to integrate this waveguide sensing and super resolution or high resolution images in the future. Okay, so I will stop here. I will thank our students and our collaborators, and I will also great thanks for the funds from NCFC and MOST. Thank you. Thank you for your time. Thank you for taking such a long time for maybe.
Okay. Yeah, thank you. Thank you very much for your nice presentation. Now is open question time. Any question to the speaker?
Thank you, Lingdong, for a very exciting talk. You do excellent work on low conversion nanocrystals. Can you show slide 19?
19.
19, 19.
Yeah, okay. I mean here or this one?
That's 16, 9, yes, here. There you see the 5 lasing lines in the whispering gathering modes, but there seem to be 3 very sharp lines and 2 broader lines. Why is that? Why are the 2 so broad and the other ones, you expect sharp lines?
Yeah, very good question. We are curious. Sometimes we can get the spectra, very good spectra, but sometimes we cannot. Actually, our experience that if you want to detect the lasing mode, the spontaneous should be depressed. So in this case, if you cite it here, you take the spontaneous emission. But if you cite it here and take the spectra here, you can get some of the lasing modes. And they are still located on the background of the spontaneous emissions. So only, yeah. Another good thing, another good question is, as you have talked, we should think why only a few can be selected, but the others still are spontaneous. We have tried. Sometimes this one is greatly enhanced, and emission is amplified. Maybe is also correlated with the wavelengths and the transition of different kinds of transitions. I'm not sure. Thank you.
Okay, thank you.
Any other question to the speaker? Any question? Just a simple question. So what about the uniformity of nanoparticle on the polysplen, the sphere?
Okay.
Yeah.
Actually, for nanoparticle, the size is smaller than 30 nanometer. We can control it to the SD. That is the size distribution can be less than 2 or 3%. But for larger nanoparticle, for example, for 40 or 50 nanometer, maybe the dispersion is larger than 5%. Okay. Yeah.
Okay. Well, any question? Okay. So thank you very much for your nice presentation, Professor Sun.
Oh, thank you. I'm sorry for taking your time. I'm sorry for this problem. Okay. Wish you can visit in China in the future. Okay. Okay. See you.
Yeah.
Oh,
thank
bye-bye.
you.
Bye-bye.
Okay. So this is the end of this session. So please enjoy lunch time and see you next section. Okay. Thank you.
所以你会再通知我吗？开始的时候你会跟我讲。对。谁？哪一个？他会先上来吗？这个他直接在看。OK。好，谢谢了哈。不会。那个演讲我改到下学期，因为我这个学期对那个细光子，因为我这个学期要上课。好，OK，好，谢谢。
So hello everybody. So I'm glad to chair this very last session of this conference. My name is Gilles Ledoux. I'm research director at University of Lyon and CNRS. And for this session, we'll have 3 plenary talks. And the first one will be given by, excuse my pronunciation, Yenxiang Fang from the Industrial Technology Research Institute. He's director there. So please.
Okay. Thank you for the introduction. I'm Yenxiang Fang, coming from ITRI, and I focus this technology over than 10 years as the pre-nitride build-up. And 15 years ago, we demoed the very high-list resolution micro display, larger than 2000 ppm for the micro LED. But you know the LCD cost is so cheap, so at the moment, micro LED cannot go up. But Taiwan face up some crisis, so micro LED maybe will be another opportunity for Taiwan industry. So every company just like AU or Polynitride, they focus and good at the micro LED mass production, especially for the TV or transparent display, even if for the vehicle display. So ITRI for now focus on the micro LED apply on AR application because due to the AI increase and the requirement increase hugely, so maybe there are some carrier just like glasses need to be adapted. So we focus on the micro LED for the AR display. So today's topic is the challenge and opportunity of AR micro LED display. So before I start this talk, I introduce myself. I say I work in ITRI over than 15 years, and over than 10 years I focus on micro LED. And in ITRI, the micro LED team is what I lead, and we get some prizes just like the Edison Award and the R&D 100. Of course, not only micro LED, we focus on the gallium nitride 35 compound semiconductor in my division. The division in ITRI we call the business unit. In my unit, there are over 90 people here. So how to make a cooperation with the industry and get funding from not only the government but also the industry is very important. So not only the micro LED, we also focus on the VCSEL and the power device and the silicon photonics. Especially silicon photonics is a very hot topic, and our government put many effort on this topic. And issue is not only the research institution, we need to get some funding from government. Besides, we need make some money. So we need to get more collaboration with the industry. So within this year, I make some contract with the industry to get a very high contract with these 2 or 3 years in each. And I graduated from the National Taiwan University on 2008. Yeah, I graduated 2008. And after that, I going on to study in EMBA in National Taiwan University and graduate 3 years ago. So this is my brief introduction of myself. And of course, Taiwan put many effort on the micro LED display, and 2 years ago, we win the R&D 100 awards and bring the honor to the National by R&D 100. This year, we win the Edison Award and also bring the honor to the National by Edison Award. So just I say in the previous slide, I focus not only the micro LED display, but also the VCSEL and power device and silicon photonics. What the common they have is the 3-5 compound semiconductor. So in my division, we not only focus the display, we also focus on VCSEL and the power module and the silicon photonics for the information. And the last slide, I will show some different application by using micro LED, especially when AI requirement increase, the highest transmission is very important. So next generation GAI or the next generation GPU to GPU or GPU to CPU, even if the HBI high bandwidth memory and link to the GPU is also need to transfer from the electrical signal to the optical signal. So micro LED will be dominant, and we will have a role on that area. Okay. And this is my outline. The first is a requirement for the AR, for eyewear. Many years ago, we can find Microsoft promote their handset, just like Microsoft handset in the left hand, just like this, but you just can wear it inside the house and cannot go take it outside because not only the power consumption but also the brightness. So after a few years, Meta combined with the mobile phone and use just like normal glasses just we wear now. And but power consumption and the brightness also the problem. However, how to really let everybody wear the glasses to not only inside but also outside. So the light and the power consumption and the brightness, the 3 factor is very important for now. And the that will over 10% penetration rate, especially using this just like a glasses stand alone or for people using outside. And this is the hand-mount display for the XR application. We know many years ago we can find HTC promote their Vive. They use the very huge wearable device and the need to some sensor wear on your hand and make some sensing. And after that, we call the video see-through, just like Apple promote their Apple Vision Pro. Yeah, but it's not real see-through. Everybody know there are two cameras. One camera is inside in the wearable device. It can capture your eye, and the other camera is outside the device. It will capture the information outside, then align the information together when you see, just like a see-through, but it's not a really see-through. We call it the video see-through. And the final product we call this is optical see-through. It really need to combine with the glass to glass, and there are some display, sensor, and transparent need to be glasses, and you can wear it, see the information outside, and can see some information on your glasses. Okay. So from the history of the HMD, many years ago, just like the wearable device is focused on the professional apply on professional industry. So the spec, because we use it inside, so the spec is not so high. Just like the brightness and the weight is very large. Many years ago, and there are some company to promote their remote wearable device just for the office and the environment uses. And the brightness less than 2,000 nits, and the weight is lower than the before. But when you want to use this wearable device not only inside but also for the outside requirement, the brightness need to larger than 3,000 nits. I mean in your eye, not the display, to inject before you into the waveguide. So the brightness is very important. For now, there is only VCSEL and the micro LED can be used and achieve this spec. And the weight and is very low. We make some research. 50 gram is also can be used for the people outside, and can be used for maybe 4 or 8 hours. And the comfort and the fancy is also important. You don't want to wear a device and outside the door and everyone find, oh, it's very strange. You are a weird man. So the comfort and the fancy is very important for these devices. Okay. So we make some investigation from many guys, and there are 3 points the XR requirement. The first is the first is the interactive. For now, we use the hand to click the information. But when you wear a device, you want to hand free. So how to make eye to click the information is very important. So eye tracking, the sensor to tracking your pupil or eye is very important. And the second one is the comfortable. Comfortable means for now, you wear the devices, even if the Vision Pro, my colleague used that over than half hour, he felt it's very heavy and a little dizzy. So how to make a comfortable and the free VAC is very important. The third important one is the high efficiency, optical efficiency. For now, everybody know not only use the meta lens, but also you use the optical waveguide, because the very low efficiency. So the panel need to be very bright, over than 10,000, 100,000. But it makes sense? Question mark. Why? Power consumption is very important. So how to make some different display is what I will talk about later. Okay. This is the common display combined with meta lens or waveguide, just like we use the traditional micro display less than 1 inch, 0.5 inch, even if some company in mainland China can demo 0.13 inch, but you need to make some reflection by the waveguide and into your eye. So the waveguide efficiency is very important. Even if for now there are 10 times improved compared with this waveguide before, the panel also needs larger than 10 times, 100 times, even if 1,000 times compared with the brightness for now, just like OLED or LCD. So we propose the different solution. The left two one is the traditional. Not only this one, but also this one. They also use just like a mirror or waveguide. The display is on the side of the glasses, and through the reflection into your eye. For now, some FOV, optical efficiency, brightness, resolution is not enough for the common people use. So we propose a different solution. Our goal is, this is the glass combined with what? One is the eye tracking solution. The second one, it need to be a transparent display. The third one is a very high resolution display. So not only efficiency, but also the heavy and the resolution embed some eye tracking sensor. What we do for now. Everybody know LED have very high efficiency because of you. For now, you use the LED for the bulb, but it can be broken. You need to use it over 10 years. So it means LED efficiency is very high. Because of the very high efficiency, so LED can be very, very small, maybe less than 10 micron. It means there are many space between the micro LED can be embedded what? Some optics and the sensor and the IC. So this is we call the micro LED 2.0 or 3.0. 5 years ago, I proposed this idea, but maybe it's not mature 5 years ago. But for now, there are many people notice it. In this backplane maybe can be transparent, just like glass or CMOS. It can integrate the micro LED for display, micro sensor, micro optics, and micro control. Because if you want to drive the micro LED to get very high resolution, redesign the IC is very important because the mobility of the TFT is so low. It can show a very high difference by micro LED. So redesign the micro IC is very important. And the left one is just I say, it's a traditional one. There are some display engine through the optics and into your eye. And there are some eye tracking sensor also integrate, but this is mini LED and is very high, or use the camera base. Camera base mean power consumption is very high. So we need to revise it. The right one is what we do. Here is what our pupil or our eye. And we have 3-layer combination. One is the micro LED transparent display. The second one is the meta lens array. We use a meta lens to be image to explore, can see the large image. And the third one is just what I said, the sensor array, eye tracker, just nearby or very close to the pixel. So these 3 layers is what we make a combination for the next generation display. Okay? And this second one, I will introduce the OE for XR eyewear. Especially many people also focus on the traditional micro LED display. Maybe the waveguide solution or some solution. The high resolution micro display is also be developed. So I will make some little time to introduce or to let everybody know what is the development in industry for the traditional micro display. Okay, we use the micro LED display by integrate or combine with the quantum dot, because when the LED is very small, especially the green or red micro LED, the efficiency will decrease as the LED less than 5 micron, especially 3 micron. But you want to get a very high PPI, so 3 micron, 2 micron is very important. So in this case, we choose very strong LED. What is strong LED? Blue micro LED combined with what? Quantum dot. So many guys know the quantum dot concept, but for now, I will make some brief introduction to talk about the quantum dot. Quantum dot are the narrow size semiconductor particle, typically range from 2 to 10 nanometer, whose optical and electronic property are distinct from those of large particle due to the principle of the quantum dot material. So when we fabricate the different size of quantum dot, we can get the different color, okay? So the basis theory is the simple theory is what we show here. When the quantum dot absorb a photon, typically leads to an electron and being excited from a valence band to the conduction band, leaving behind a hole. This process creates an electron home pair, which can bind together to form a exciton. When exciton recombine, meaning the electron return to its ground state, the energy of the electron can be emitted as a light. So this is the basic theory of the quantum dot. And there are many products, just like I show in the slide. Understanding this fundamental principle allows us to harness the unique property of quantum dot for a variety of applications, especially display technology like QD OLED or QD Mini or QD Micro LED. By precise controlling the size and the synthesis condition of quantum dots, we can create displays that are bright, more efficient, and capable of producing a wider, vibrant colors. Okay. And in the early stage of the micro LED, there are many transfer technology to be used, just like micro LED combined with the quantum dot. You can use the red, green micro LED, and there are 3 blue micro LED, and the quantum dot can be put on the blue micro LED. And when the blue micro LED make an eject, it will show the green and the red. And the other technology to make transfer, we call the stamp transfer and the laser selector. So for now, there are many people focus on the different technology. Even if the Taiwan famous company, they can combine with the stamp, selective laser, even if the micro quantum dot. And many years ago, when you use a quantum dot, the PPI is very low. It's less than maybe 10,000, and the panel size will larger than 1 inch. But as the time passed, the technology improved. So for now, we can find that this blue blue one. The PPI can be over than 10,000, and the panel size we can be less than 0.5, even if 0.13 inch. We use less than 3 micro LED combined with the quantum dot to demo the 0.13 micro display. This is what we demo in the paper and in some conference. So when you use a quantum dot, there are two methods. You can use the lithography technology, or you can use the inkjet printing. So in E3, we use the inkjet printing and the QDPR both. For the inkjet printing, for now, the size is around 5 micron, and pitch is around 6.4 micron. But when we use the QDPR means integrate the QD into the PR. So when you use a high resolution lithography technology, the size can be very small. So for now, the pitch is less than 5 micron, and the size is around 4 micron by 4 micron, and the PPI can be over than 6,000 PPI. Here we would like to share our recent study of the 0.49-inch micro display. This is what the spec is. Because of the different PPI, not only the size but also the resolution. There are different spec what we achieve for now. Over 6,000 PPI. We also demo, but the size is 0.49. And we also the 0.13 inch single color panel, but this is confidential of our partner, so I just let you know. But the size for now can be down to 3/2 to get a very high resolution. Okay. The other one is the reliability. To consider the lifetime of QD, also QD are not as sensitive to water and oxygen as OLED, then they still have organic ligands surrounding them. These ligands can degrade over time due to prolonged exposure to blue light extraction and heat. This degradation can lead to the ligands losing the efficiency, causing the quantum dot cold to become exposed, which can result in oxidation or reduce the efficiency. Therefore, a more effective approach is to apply a moisture and oxygen barrier layer to prevent exposure to air. It's very important. In collaboration with the National Chiao Tung University, we had used ALD, atomic layer deposition, to coat QD with aluminum oxide as a protected layer. We conduct burn-in test at 50 degrees C and 50% humidity for over 300 hours. The results show the under protection of aluminum oxide, the PLQY, conversion efficiency, degradation of QD was less than 5%. The impact on color gamma value was less than 1%. But I mean just the blue and the green quantum dot. The red quantum dot has some problem. It's also be solving for now. Okay. The second one I will introduce our another technology is the meta optics. We call meta lens. So just I say we have three layers. The first layer is the display, and the other layer is the meta optics, and third one is the sensor. And after we do these three layers, we combine together. And when you see the view of outside, you can see the information here and also see what the spice is outside. Okay. In typical waveguide, the left one, XR gases, the display panel mainly consists of a microdisplay module integrated on upcoil CMOS backplate. The display image are coupled into the optical combine through an input coupler and through an output coupler for human eye reception, enabling simultaneous viewing for both environment and the virtual image in XR application. However, the low optical efficiency, especially the waveguide, maybe less than 1%, everybody know that. So the waveguide necessitates micro-display panel with very high brightness, usually higher than 1 million nits. It not make sense because of the power consumption. For outdoor application, furthermore, the display panel resolution is limited by the panel size, usually less than 0.2 inch, imposing stringent requirement on manufacturing capability. There are the two bottlenecks that micro LED face when introduced into XR glasses application. Therefore, we intend to fundamentally overcome existing framework limitation by modifying the optical engine architecture just on the right-hand side. The main principle involves dividing the upcube micro-display panel into multiple small micro-display blocks arranged with a parametry, and the block structure can be turned as island. The size of each island is approximately 300 micron by 300 micron, which such small island structure being imperceptible to human eye at a typical wearing distance, thus not obstructing the field of view. Additionally, these island matrices are periodically spaced on the glass lens when blank area between adjacent island maintain overall transparency about 70%, suitable for see-through requirement XR glasses. Lastly, individual display region can be optically colliminate and diffract through meta lens and form a full image on the retina, thereby completing the overlay of virtual image onto physical environment in XR application. So this is what our transparent micro display prototype. Based on the above, we have developed a prototype of island matrix transparent display panel for demonstrating the functionalities of direct view optical engine. This prototype initially employs a passive matrix-driven architecture to expedite the panel's integration and verification. The red box highlights a single micro display island, magnified in the image below, comprising a 20 by 20 array of micro display, micro LED pixel. Meta ring connects this pixel in both raw and current direction to the driving circuit. The right image illustrates conceptual resonation of the island matrix transparent display panel. Within the effect display area, there are 7 by 7 dispersed independent island matrix blocks. Okay. So for now, the current one is here. They are the micro IC is just around this display, and the micro LED is here. But in next or 3 generation, we will put the IC outside the pixel and the display only the LED. It can be easy to be repaired. So these 3 generations It's just what we focus now. Okay. The design of the meta lens component has the function of collimination and the deflection used to project the light from a pixel of the corresponding micro LED island onto the retina, okay? And by arrange meta lens component with various diffraction angles to form a meta lens array module, the display image of each discrete island can be magnified and distinct into a complete virtual images. Okay. This is our really data. The lens array in the optical engine is designed with 49 elements, corresponding to transparent display panel and a feature 3x3 display islands. Each display contains 20 by 20 micro LED pixel, which one lens component corresponding to one display island. Each meta lens element in the array has a different diffraction angle direction. Hence, the design pattern of their optical phase difference distribution also differ observing the pattern produced by the manufacturing process under backlight illumination. The meta lens exhibits feature consistent with its design pattern. Okay. The third part, I will introduce our eye tracking. The left one is the traditional eye tracking. You use the CMOS image sensor, so the power consumption is very high. The right one is what we do by micro LED solution. So on the sensor-based eye tracker detect on the right-hand side the signal difference in eye movement reflection through photodiode on a frame and use regression models to predict the gas point location. Although the sensor-based eye tracker doesn't use image analysis and have slightly lower range accuracy compared to camera-based, the left one, they have the advantage of faster update rate, low power consumption. So depends on the area what you use. If your trial area you need to high accuracy, you can use the CMOS image sensor technology. But if you want to just use the easy clinking, so low accuracy maybe can be adapted. So the right hand side is what you choose. And the algorithm principle of sensor-based eye tracker involve first collecting sensor signal from 6 gas points on a screen direct in front. These data points are used to train a regression model. Once the training is complete, the regression model can be used to predict the gas point location of the new data. This is what we really show now. You can find, when you find this one can be clicking. If you see this one can be clicking. The left one is the comparison compared to the traditional CMOS image sensor and our eye tracking sensor on the glass. Okay. The next part, I will show some platform and some other application. For now, E3 set up this micro LED lab over 7 years, and our lab is class 10. So we can do very small micro LED down to 3 micron. Not only the chip size process, but also the mass transfer. We use a different mass transfer, depends on what the product you do, okay? So this pilot line can be applied and can be used for all over the world or some company interested in this lab, okay? And this is what we show. The left one is the LED. The middle one is the we make some transfer. The right one we demo some transparent display or AR or signage. Last, just as I say, micro LED can be used for the AR, but not AR application, because the very short transmission. Micro LED have enough transmission rate. But you can see the VCSEL or IMP or some PCI electric, the transmission rate is larger than micro LED. But micro LED can be an array. So if you use 10 times, 100 times, the transmission rate will increase, especially for the link it to the GPU to GPU, GPU to CPU, HBM to the GPU or others. So for now, we also development combined with the some system guy in Taiwan. Okay, so they are not only use many micro LED, but also you need to use many micro PD, and this is the what? Not only the single fiber. Is the multi-fiber, because there are many micro LED here. So when the micro LED inject into this fiber, there will be many multi-core, multi-fiber. So there are three key points. One is the micro LED array. The other one is the micro PD. The third one is the multi-core, multi-more. Okay? And in this case, we just only use less than 1,000 micro LED. So 1,000 micro LED to use mesh transfer is very easy, especially for a pre-nitride or a P-star or something else. So micro LED has very potential to apply on AI application. Okay, this is my next slide. So each will have many customized service, not only do the prototype or a patent or some new project, we can make some POC. So if you are interested in, please contact with me. Thank you.
Thank you. It's now open for discussion.
Well, thank you for sharing some very interesting and exciting work. I have a question about the stabilization of your quantum dots that you do with ALD, I understand. How does that affect the absorption strength of the quantum dot layer?
Pardon? Please?
How does the stabilization layers of the quantum dots affect the absorption strength of your conversion layer?
Oh, you mean advantage by using quantum dot? I think if you want to get very high PPI, especially you use the traditional display combined with the waveguide, the micro LED need to be very small. It means only the blue micro LED can be strong. Especially, however, the red micro LED is not strong. So when you use a traditional solution, micro display combined with a waveguide or bird base, you need to get very high PPI. So LED will be down to 1 or 2 micron. At that moment, blue micro LED is the only your choice. So combined with the quantum dot, will have some advantage when you get very high resolution micro display. Okay.
Okay, interesting. Thank you.
There are other questions? So from my
So concerning the point of view, in your slide you say the micro LED will save the power, so that means save the energy. But I heard from some of the people, they criticize micro LED could be more power consumption than the conventional LED. So can you give more comments on this?
Good question, but depends on different application. If for a transparent display, only micro LED can do the very high transparency. Even in the LG, only the 50%. If you use a micro LED for the vehicle, OLED can be achieve the spec. Why? Because of reliability. Some car use the OLED for the display because of they downgrade the requirement in vehicle. So reliability in vehicles is important. So micro LED can be used on vehicle. And the other one is I think the power consumption is more important in the AR. But if you use the traditional micro LED display, I mean maybe you use a 3-color micro LED transfer or one micro LED combined with the quantum dot, the optics need to be solved first. If the optics can be increased from 0.1%, 1% to over 50%, micro LED, the brightness can be lower, maybe 10 times. So the power consumption advantage will happen. So depends on what you see. If you use a traditional micro LED display for the AR, I don't think you will have the very low power consumption advantage. Okay.
Thank you. Okay, thank you very much. I don't think we have time for more questions, so we'll go to the next speaker and thank the speaker again.
Thank you.
So next speaker is Sheng Yuan Sun, who works in director at Play Nitride company. So please.
Okay, good afternoon, everyone. Firstly, on behalf of our company, I want to give the great thanks to the Professor Liu Ruxi and Professor Lin Junzhen. Thank you for giving us this opportunity to join these important activities. I'm Neil, and one of the co-founder of the Play Nitride. And now, I'm in charge of the optical R&D development and also glass-based micro LED panel business. Actually, it's really high pressure to give this talk after Dr. Fang. Dr. Fang is the well-known expert in micro LED field. So I think people like you have already learned about micro LED from him. So now just in the coming 30 minutes, just let me give some introduction about our company and our achievement. Okay, what's the micro LED might be the first question for some people unfamiliar with this technology. You can think of the micro LED as the traditional LED, but the scale is down to the micro scale. Just like this one, it could be achieved by removing the substrate and reach the dozens of micron, even several micron. So you can see the video, it shows how micro LED light on. And we have already known there are a lot of LED applications in our life, just like a solid state lighting, LCD backlight, and also video wall. As our experience, LED was used based on their advantage, just like high efficiency and also reliability. And when we downscale the LED to the micro LED, we can get several advantages. The first is the lower power consumption compared to LCD. Micro LED only needs 10% power due to the self-emission feature. And the second is the higher brightness. You can read the information under the sunshine if you use micro LED. And it could also provide very low brightness, so it can deliver high contrast. And the ultra-high resolution could help to build the metaverse. We already know that the PPI can be reached thousands for the micro-display application. And since micro-LED made of the inorganic material, it can offer long lifetime and a wide operating temperature range, which is the desire of the automotive display. And fast response would be the basic of the high-end gaming application. It only takes nanoseconds between the switch on and off. And also, the last one is the thickness. It's because the simple structure of the micro-LED, which allowed the panel thickness, could be the 1,000 micron. So enabling the flexible, reliable, and the foldable display. So based on this advantage, we can design the micro-LED into 3 major solutions for different applications. First is the micro-LED on PCB, which is designed for the large and the brighter display. And the second is micro-LED on glass, which is designed for the transparent and flexible display. And the final one is micro-LED on silicon. It's for the AR micro display and projector display. So, I think people might ask, how to make it? Because the micro-LED is so small, so we make micro-LED easy to be transferred on the backplane. Just like Dr. Wang said, we can bring the micro-LED chips onto panel for thousands or more. So in the beginning, we produce the chip on wafer and transfer the RGB 3-color chips to the temporary substrate. We call it COC, chip on carrier. And we use the mass transfer technology to mount the micro-LED on backplane from the different color COC. And also, we can help the customer to put these 3 colors chips into the same temporary substrate. We call it COC2. And it would be much easier for customer to use. So not only the COC and COC2, we can only provide the micro-LED in packaging, we call it MIP. It's for the customer which is not familiar on the mass transfer technologies. They can use the traditional SMT technology to put the MIP and the IC on PCB to become the modules, and also assembly several modules and with receiving card and the power supply into the Cambium. And then they can install the Cambiums with the video processor and the controller to the micro-LED display. So, because micro-LED is simple and robust, it could be designed as seamless and can be tiled. So if you have many micro-LED on PCB, you can make a bigger micro-LED display, just like this one. We used the 168 pieces PCB to make 89-inch 5K resolution curved micro-LED display. Okay, so we can use this product to build a professional and better LED world for virtual production stage. Here, I just have shared some pictures and the samples for you to think about this application. You can see many big LED world are surrounding the actor and the stage purpose. So we can think, if we can use the micro LED in here, you can get much better visual effect. And another incredible micro LED display is a transparent display. We created the first transparent micro LED panels and demonstrate it in the 2019. Even there are 1 million, it's around 1 million micro LED chip on this panel. You still can see and know it can see through, and the transparency is very high. You see, you just put the camera on the transparent micro display in the front, but you still can see the mountain view shown behind this display. And then, this year, Samsung demonstrated the tiled transparent micro LED product. So let me just share a good video with you.
Hey everybody, I'm here with Samsung, and here's some of the coolest things that they're doing this year for television displays in 2024. First up, micro LED transparent. That's right, Samsung has invented a way to actually see through the micro LED to the other side. So micro LED displays, in case you haven't been paying attention, Samsung uses in their massive wall-sized televisions, basically millions of tiny little LEDs, super bright, great picture quality. So now they're making a transparent version of those screens. So the idea is you look through the screen and you can see whatever's behind it, and meanwhile what's on the screen is brighter with better color than what you get from other transparent technologies, namely transparent OLED. So transparent OLED has been around for a while. It's a little bit dimmer from this demonstration that I've seen right now than transparent micro LED. And so it has that advantage, micro LED, of being not only brighter, but also having better transparency, so you actually see through a little more. Now, transparent displays, not really the most practical thing, but you can imagine, for example, behind me, Samsung showing a sports stadium scenario where you're sitting in a skybox and you're looking through the glass and you have the scores and everything kind of displayed on the screen in front of you. Behind is the actual event itself, which is pretty cool.
Okay, through this video, people might want to know why micro LED can reach so high transparency. This is thanks for the simple structure of the micro LED. And here you can see, according to the side view of the LCD, it's complicated. There are so many layers needs to build for LCD for the full color image. And OLED is better, but you can see micro LED only needs a substrate with the circuit. No need a backlight, no need a very careful packaging. It's really simple. So you can see this picture. This is a picture I took last year when I go to the Angels Stadium for Shohei Ohtani. So you can think about it. If I watch this game in the VIP rooms and the window is transparent LCD, it will look like this because the transparency is really low due to the BN and the color filter. And if they use the transparent OLED, the transparency will be better, but the brightness is low. So, micro LED is the only good solution for these applications. It's because the most of emitting area in micro LED is the emitting area of micro LED is small, so the open ratio is high. So it also leads to the high transparency. And here, the automotive market is also beginning to adopt the micro LED display. In 2018, PlayNight have really demonstrated micro LED panels in car models for different fields, just like the HUD, rear view display, and A-pillar display. And this year, AUO also demonstrated in the active transparent window and the rollable seat entertainment display by using micro LED. And the Continentals demonstrate the CID display by using the transparent micro LED with Swarovski crystal. So just let me share a video with you. This is the rollable. And this is transparent. Okay, so because of the simple structure, the micro LED can be made as a thinner display. We demonstrate a transparent and flexible display, which is only 28 microns thickness in 2019. And after that, we collaborate with our partners to make the bigger and the flexible micro LED display. So just like this one. Especially, this technology can be made as a rollable and attached as a sketchable display. However, it's not easy. You can see here, if we just follow normal the circuit design, the circuit will easy to broken. So it needs a special circuit designs for a stretchable display. For example, kirigami is a kind of the folding paper art in Japan. In kirigami, the papers can be cut as well as being folded, resulting a 3D design and doesn't need the glue. So of course, we can use this traditional art idea to design a substrate for the micro LED stretchable display. Of course, that's also important is because micro LED, the emitting area, the size is really small, so you can use that. So in the passing years, we have really demonstrated many different types of the micro LED display with our partners. And also, we won a lot of awards from this demonstration and with our partners. And this year also, we won the best micro LED technology by adjustable transparent micro LED display. We just only need is put the transparent micro LED in front of the adjustable liquid crystal panel. So, when the liquid crystal light off, it's transparent for visitors to see the content. And when the liquid crystal light on, we can get good image qualities by high contrast ratio, high brightness, and the wide color gamma. So, people might ask, when we can get this super, almost perfect display in the market? The answer is now. So if you search the micro LED product, you can see so many different size micro LED TV. Our company just purchased the this one, the 89-inch, the micro LED TV, and put it in our lobby. So if you have interest to see how incredible it is, please come to visit us, and I will show you. However, even you can see it in the market, it's really not easy to put it in your shopping cart because the price is amazing. For example, the 89-inch micro LED TV we got, it cost more than $100,000 US. And you can get similar sized LCD, but it only needed 1,000 US dollar. So it's a 100 times difference. So the more important question is how to reduce the cost. We can find some way through the micro LED technical flow. Here you can see plain nitride core technologies are shown in blue part. We are working on the wafer epitaxy, chip process, COC, and the mass technologies. Mass technology also included mass transfer, mass inspection, testing, and repair. So I think we can start from the wafer epitaxy and the chip process part. First of all, I think we need to improve the wafer yield. By reducing the particle levels, we can get higher yield, and it will lead to the lower cost. And if we get the higher uniformity wafer, higher usage also lead to the lower cost. And people also think larger wafers will also lead to low cost due to the higher area usage. So some of you might think about why don't just reduce the chip size and get more chips from the same size wafer? So we can see here, it's because when the chip size was be reduced, the efficiency will be also reduced. But by our technologies, we can put it back, we can improve by improving the chip process to reduce the defect and bring the efficiency back even better. And also, the red is, but about the green parts, you need to work harder. So we can know higher efficiency chips will also lead to the lower cost. Okay, we can try another way. When we say high efficiency chips also can lead to the low cost, we can also do a lot of the structure and also optical design to increase the efficiency of the chip itself. And it will be useful to reduce the cost. Okay, and then the next is the mass technology. So we can design a suitable COC to develop suitable transfer machines for the mass transfer. Because in the beginning, when we create a COC, we provide the suitable different type of chips to our customer. They think, okay, they get a wafer, but they don't know how to do the good transfer. So we start to redesign the transfer machines, and we can tell them, okay, if you purchase our COC, we can also deliver the suitable transfer machine to you. So you can see here, compared to 2 years ago, our transfer speed has already improved to more than 10 times. And the full HD display only takes 24 minutes to produce. So it also means the process cost will also be reduced. And the final is the module. So not only by improving the chip efficiency, but also we can improve the efficiency of the module. And then we can use the smaller chip to reduce the cost. For here, you can see we designed a different optical structure, just like the micro lens, and we can use this micro lens to improve the efficiency of a total module. And also, I think, especially, I want to mention here is the quantum dot color conversion. This technology is very, very important for the micro LED. Based on the higher efficiency in the lower driving area, the quantum dot color conversion can produce high efficiency AM driving panel. So here, just let me share some time to describe about this one. For the first study, we are the company making the red, green, and blue chip company. And we find the epitaxy system is totally different from the red and the green and blue. So we can find that the efficiency curve is totally different. Just like in the left side, you can see we share the efficiency curve of the red chip. It's the red one. You can see during the lower driving area, it's low. But when we put the quantum dot color conversion curve on it, you can see quantum dot color conversion is much higher during the lower driving area. And of course, you can think we put the quantum dot on the blue chip. So this curve structure is almost like the blue efficiency curve. So if we improve the efficiency of the blue, we can also improve the red quantum dot color conversion red chip at the same time. Okay, and not only the efficiency, but also the quantum dot color conversion can show less decay when it was be driven under the higher temperature. That's the other disadvantage of the pure red chip. Because normally red micro LED chip, when it was be driving on more than 60 or 80 degrees, the efficiency will decay very fast. But compared to the blue micro LED chip, it decays slow. So you can also think the quantum dot color conversion red chip made by blue chip, it will decay slower. So compare these two, we can know by quantum dot color conversion technologies, we can produce very good quality red pixels. So we can also reduce the cost through this technology. And not only the efficiency, but also we can find that the transfer time could be reduced because we don't need the red chip. Even we only need blue chip. So when we add the quantum dot material, we can produce full color quantum dot color conversion micro LED display. It also means the process cost could be reduced. However, the real challenge is just the beginning. Even polyethylene nitride, we know a lot of the key solutions to reduce the cost, but it still takes time to reach the reasonable cost by only our own self. Especially the market will grow so fast in the coming years, based on the predictions of many analyzing organizations. So if the developer of the industry is slow, the bigger challenge we will face is not the micro-LED technology, but the market share of other growing display technology, just like OLED. So we need to cooperate with our close partners to speed up micro-LED. So based on this one, we proposed a solution. We offer the turnkey solution to our partners. We provide our technology and to partners with the strong financial capabilities and assist them to set in the micro-LED production lines. So by this model, they don't need to waste the time for initial research. And then we can prepare the production capability together for this work. And this can help to reduce the cost and push the mass production of the micro-LED. So if you have already searched for news, you can know it's already happened in the past years. And not only COC and COW, but we also start to provide our own mass transfer machines to the customers. And anything else we can expect for the long-term market. Okay, just like Dr. Fang mentioned about, micro display made with the micro-LED is the best one we can see for the AR glasses and the metaverse. So, even there are so many challenges for the micro-LED, micro-display, you can see here, there are several ones. It's just like, okay, the bonding technology need to be improved, and also the chip quality need to be improved, and the uniformity issues need to be improved. So we still can make some important improvement by this one. For example, we have really increased the brightness from the 50,000 nits to the 300,000 nits. And not only the brightness, but also the color gamma and the pixel yield were improved by our technology. So we can provide high quality, full color micro-LED micro-display demonstrations. Just like this. The video I show here is recorded from our micro-LED micro-display. And you can see it's almost perfect. So if you have interest on these demos, you want to know how it looks like through the glasses, please come to visitors, and I will also show with you. So I believe when you put it on, you definitely have more confidence on micro-LED. Okay. So just let me give a quick introduction about the platinum nitride. We were founded in 10 years ago, and now we have around 500 employees who work with us to create a micro-LED business. And our headquarters is in Hsinchu Science Park, and there are some offices are located in Tainan and Taipei for some special tasks. And also, since this year, we started to serve the North American customers from our San Jose office. Please come to visit us if you just pass by there. It's around the San Jose airport. And we also built the first micro-LED production lines and support our customer to provide the first micro-LED commercial product in the world. And in 2022, we become the first company to trade on the Taiwan Innovation Board. Until today, it's around 17 companies in this innovation board. So people think that we are one of the leading companies of micro LED. But some people think that we are the ecosystem generator of the micro LED. So you can see our patent application have already more than 800. And it's not only located on the one area, not only on chip, not only on modules. It's covered the entire micro LED ecosystem. So just let me share one video with you to know more about the plain nitride.
What does the future look like to you? Displays will be integrated into daily life, and people will enjoy smart lives with high-tech assistance. The question is, how long will it take? The future, in fact, is clearly visible. As micro-LEDs move from theory to product, they're constantly being called the ultimate display. Micro-LED watches, as if wearing a computer. It has high-resolution performance and over 2,000 nits brightness, completely free from sunlight interference. The ubiquitous micro-LED advertising signage board, with a three-dimensional vivid borderless performance, allowing all practical technology combined with art to become a smart street scene. Interactive transparent micro-LED display. Every piece of glass can convey the message. High resolution and high brightness tiled micro-LED large signage. It can display speeches instantly, regardless of the size and shape, indoor and outdoor. And the tiling feature allows the signage to be replaced when it's damaged, without waste of electricity, which is extremely environment friendly. The future of the automotive environment, whether safety or entertainment, relies more on the assistance of panels. Front bezel, side windows, sunroof, dashboard, center console, and trim panels are all excellent locations for micro-LED displays. Micro-LED AR glasses. It makes the entertainment in front of you come to life. These are realized by the following micro-LED features. Low power consumption. Compared to traditional LCDs, micro-LED consumes only 10% of the electricity, and the technology is eco-friendly and energy-saving. High resolution. The size of micro-LED is extremely small, allowing it to be lined with more micro-LED chips to achieve higher resolution performance. High brightness. It's not disturbed by ambient light or sunlight, and can even be used as a light source. Stable reliability. Same as LEDs, micro-LED chips have a lifetime of tens of thousands of hours. Compared to traditional LCD screens and OLED displays, micro-LEDs are thin and light in structure and can be bent or presented transparently with a backplane to show different states of bending, and can also be used as transparent displays. No latency in response time. Delivers lag-free screen switching. From LED wafer fabrication, enhancement control of uniformity, micro-LED wafer generation, to mass transfer and repair technology, Play Nitride has the core technology capability and solutions for various applications to produce the ultimate micro-LED displays. Located in Hsinchu Science Park, Taiwan, Play Nitride was established in 2014, gathering a group of partners who aim to change the world and bring new ideas to the nitride industry. After years of hard work, Play Nitride established mass production lines and a complete R&D team in 2019 to provide complete solutions from epi-fabrication, die splitting to mass technology. In that year, we started shipping to customers and became the world's first leading company in mass production of micro-LEDs. Since 2018, Play Nitride has been introducing new solutions at annual exhibitions and won various awards for micro-LED products and technologies since 2020. In the process of improving R&D and yield rate, Play Nitride has also been protecting its intellectual property rights. As a leading micro-LED company, Play Nitride has not only signed industry-academia cooperation projects with universities, but also cooperated with ITRI to improve the technology. As the company grows stronger and more complete, the establishment of CSR, an employee welfare system, is also one of the projects planned simultaneously. In order to implement the company's innovation spirit and competitiveness, the company organizes various sports and team competitions to motivate employees to maintain a high level of activity, and establishes the Play Nitride Academy to invite famous representatives from various fields to give lectures and share their experiences to enhance employees' vision and knowledge. CSR is deeply rooted in the daily lives of our employees, and ESG's sustainable investment in various aspects of social feedback, from beach cleanup activities and charity fundraising to the company's friendly welfare policy, encourages employees to participate and enliven the company's atmosphere, while enhancing the richness of employees' lives, so that life is not only about work, but also the spirit of giving back to society. In the future, the demand for micro-LEDs will explode. Play Nitride has unlimited potential for continuous growth. Join us and see a better future.
Okay, sorry, because it's too less time, so I only have 35 minutes to share this one. So this is our last slide, and we will hold a micro-LED forums in the beginning of September. So if you have more interest, you can join this one. Thank you. I'm Neil. Thank you for your attention.
Thank you. So we only have time for maybe one quick question, if there is any.
So you mentioned the blue transfer to the quantum dot is quite efficient, but can you give a comments on the technology of the UV transfer of the RGB they all use for the quantum dot? So any comments for this kind of direction? Thank you.
Okay, thank you. I think this is a very good question. So in the beginning, we are RGB pure chip companies. So we just doing some research on quantum dot color conversion in the beginning. But during the past years, we find out some amazing result. Because in the past years, we not only research for the red QD, green QD, we also think about, okay, UV chips to pump in RGB quantum dot might be a good solution for R&D. Because when I used, in the beginning, I used the UV light to pump in the red and the green QD. It's very bright because the efficiency is very good. So we also propose this to our CEO and also our customers. But they think, okay, they can understand through our description about this proposal. They can also understand only UV and only one times the mass transfer, and also you can get much higher efficiency. But the customer we faced, they are doing product to the consumer devices. They are doing much applications for human eyes. So all they're considering is how you avoid the UV light to damage people's eye. Even, okay, you can promise, you can provide a 1 million display, but if only one panel is failed, it's very important issue for our customers' brain. So they think, okay, it's a good result, it's a good research and a description about this technology to use the UV, but they cannot accept this one because it's too high risk for them to provide this kind of product to the market. Thank you.
Yeah, so now we'll pass by to the next speaker, but first let's thank the speaker again. So the next speaker is Professor Dae-Young Swin. Jean, sorry, from University of Technology of Sydney and Eastern Institute of Technology in Ningbo. Please.
Hello? Okay, that's great. I think I'm very lucky to be the lucky last. I enjoy the conference so much, and I would like to take this first minute, express my attitude and gratitude to Professor Ruxi Liu, Professor Lin Chunzhe, for the nice, very hard work inviting us to Taiwan. And we really enjoyed the last couple of days with all the international community people. As the last speaker, I think my title has been changed from the proposal a little bit. I added an affiliated title called Powered by New Devices and Instruments. Because in the past few days, I think most of the topic been focused on the fluorochrom's, phosphors, the material science and properties and application, etc. I think one thing we haven't emphasized strongly is the characterization. How can we build instrument, or how can we develop instrument that allowed better characterization towards the desired application? So my talk today is pretty much focusing on the devices and instrumentation for the last more than decade by my team of students and postdocs. How can I flip the... Right. So very briefly introduce my institute and my university. UTS is exactly in the middle of Sydney, so like 2 minutes walking to the central station of Sydney, so very convenient. UTS is one of the top 100 universities in the world, and is very strongly focusing on the technology. And I joined the university for almost 10 years. By early next year, it will be 10 years. When I joined the university as a chair professor, I gave a proposal to the Vice Chancellor. I said, as a technology university, how can you link science and technology? Because I identify a very good opportunity to translate the advances from the material science and photonics into biomedical applications. So in the past few years, the great team, make a lot of success, and I'll give you some aspect of the success we made. Particularly when you see this institute was formally launched 3 years after I joined this university, and Professor Stephen Chu, who is at Sydney for 1 week, and joined this celebration. There's a very true belief in the bottom of my heart. In the other word, to do a good job, artisan is a best tool. And this is from Confucius. That means, we need to spend more time on the instrumentation itself before we can realize a good project. So my talk today, I will cover 3 aspects of research into 3 basic directions that basically can capture most of the audience today. So the first direction is on lengthening complex. We heard a very good talk on this conference, several good talks, talking about lengthening complex, lengthening cheilets. Gary and Mickey also presented yesterday. I will show you how we develop the time-gated luminous flow cytometry, microscopy, and spectroscopy that give you a better data when you characterize this sort of material. Then the next one is my hobby, of research called upconversion nanophotonics. So this is a sort of organically, inorganically doped, lengthened doped nanoparticles, and we developed a couple of different instrumentation that lead to new property discovered and commercialization opportunity as well. Then the recent one called near-infrared bioimaging instrumentation is really the trendy topic when people try to shift the wavelengths, excitation emission wavelengths from visible to near IR. So this is all, hopefully all related to your research. Starting from my PhD, and my PhD was 20 years ago. When I started my PhD, my supervisor, Professor Jim Piper, said to me, your PhD should challenge very different things. Your PhD should end up with a patent, not a lot of paper. We need a good patent and towards the commercialization. So this is really highly inspired by my PhD supervisor, Professor Jim Piper, who sadly passed away, last July, almost 1 year anniversary. So I would take this opportunity to, acknowledge his great, supervision and mentorship on my career. So that time, I developed a time-gated microscopy means, flow cytometry means we apply the long-lived luminofluorochromes into the rapid flow so that you excite the flow by LED. This is a traditional UV LED we applied because the lanthanide complex absorb in UV 365. So I built this entire flow cytometry system, including microfluidics, the optics, electronics, and also the data analysis. And this is some data I haven't really published. This is by the end of my PhD. I tested the detection limit. When you quickly run each single microbeads, 5 microbeads, no problem. 1 microbeads, no problem. Even half micron beads, containing European complex in the beads, when single beads, they're passing through very rapid fluidics at a speed around 3 meters per second, which is really quick. I can quickly count thousands of beads individually per second. And then you give a statistical result of the distribution of these beads. Then in parallel, I also developed some time-gated microscopy because normally fluorescent microscopy, you got the dichroic mirror, you separate the excitation wavelengths from the emission wavelengths so that you're using color filter to separate the different target. In time-gated microscopy, which take advantage of long-lived fluorescence because most of the phosphors these days, they have a long fluorescent lifetime. Even the LEDs, when I start my PhD, I try to use LED to excite my sample, but I found the LED has a lot of phosphor emissions, so we characterize the phosphor emission from LEDs. But in this case, we use a lanthanide-doped European nanocomplex so that they have hundreds of microsecond lifetime. Then you can add a optical chopper on top of the eyepiece, and you synchronize the LED with optical chopper. You can remove all this background fluorescence. In this case, it's a real-time video results you can get from a eyepiece. Basically, this is exactly what you see from the naked eye. In the image is the Giardia, which is a parasite you label by European complex. You can see this is really powerful to remove all the autofluorescence background, and that provide a background-free condition, which is much better than filter, because in filter, you still got other sort of red fluorescence that interfere very strongly with your target. And this is the protocol, after my PhD, and I write down all the details, and this is published, and anybody can follow the protocol. But if you don't want to follow the protocol, you just want to use the technology, and these days we have a commercial unit, and we assemble together, which you can just attach to your inverted or upright microscope so that you can have the time-gated application. This is a collaboration with a group in Dalian University of Technology. They've been using my microscope for more than 10 years. They generated more than hundreds of different papers using my microscope, and still there, very, very robust. In this case, you can do single-cell imaging and tissue imaging and small animal imaging. Two very latest results we just published in the last few months because most people know me. We're doing a lot of up conversion, but this area or this direction we never stop. So a few months ago we published one result which we use a dendritic structure to link the multiple BHCCT European complex, so that we want to amplify the results. So that you can see from this amplification, the lanthanide complex has better advantage in terms of the concentration quenching, because the excitation spectrum and the emission spectrum, they are well separated. So even you bring two lanthanide complex close enough, they never self-quenching. So this is something, some advantage. In that case, you can add a lot of lanthanide complex into one probe, and in terms of antibody, you can use this probe for intracellular microRNA labeling and application. So using the time-gated immersion, you can see this is non-time-gated and time-gated, which provide you much clean background information. You can quantitatively count how many dots in that inside each of the cell, so that you know how many single microRNA are there. This is a very quantitative technology we developed. Also, you can see this is also you can apply for large tissue. So this is in tissue staining, time-gated and non-time-gated. The other one, in parallel, we developed a Laboda approach that uses a DNA barcode to amplify the signal. So you have 2 stages of amplification. Once you have single viral RNA, and this is really inspired by the COVID-19. At the beginning of the COVID-19, I inspire my students what we can do to save the world, what we can do to resolve the problem. So one proposal said, we can do the in situ imaging and to count how many host cells get affected by the virus. So then we developed this probe, and we can highly concentrate multiple European complex, and this complex specific to recognize the viral RNA inside the cell, so that you can quantitatively count, the chance how many virus actually get infected, infected the whole cell, and you can do the quantitative imaging. Because the results have been published, so I glance through very quickly. Not only do, one by one counting, you can do high throughput scanning. So this is more than 10 years ago, we're adding an automated stage so that you can scan the results, and you can read any single point. You can get in time result signal to measure the lifetime. Also, you do the surface quantitative study of the surface antigen, and this is old work. The other direction is because we know the lifetime, we know how to handle the lifetime, and that's really where getting me into this field. To me, it's a new field, but into materials community, it's been well developed for several years and called up-conversion nanoparticles. Once we come to this field, we found there's a lot of opportunities for the instrumentation characterization, developing new modality, and finding the new properties for new applications. And this is all the list of top quality publication, basically by my group, which is crazy. But the reason I said this is plenty room. You still get plenty room to publish high quality publication, getting really fascinating for science with up-conversion. In a nutshell word, what's up-conversion? Up-conversion is you can combine multiple low-energy near-infrared photons into the visible photons and even the DPUVs. And recently, we demonstrate you can pump 6 near-infrared photons into 1 UVB emission from the particle. Up-conversion has many properties. One obvious property is you pump from near-infrared, you're getting visible, and you've got very sharp emissions, which is characterized by, in this case, is erbium, because of multiple metastable levels, and each level, they have long lifetime, which is the characteristic we really love. So that's where we're getting into the up-conversion community. But after that, we found there are many, many very unique opportunities we're still developing from this list. There are many, many unique properties. I'll go through very quickly, how we built the new instrument, and then we found the new opportunities, and we developed new applications and towards a new direction for research. The first one, when we first came to up-conversion, we thought, there's a big challenge because everybody complained the low yield. And that time, people say, the up-conversion quantum yield is 2% or 3%. For nanoparticle, could be 0.2% or 0.3%. How possible you can use that, right? But because by physics training, my background is basically photophysics, I think brightness and quantum yield, they are different. A material, they have a high quantum yield, yes, they deliver better brightness, but not necessary condition. So you can develop other parameters which make your single nanoparticle bright enough. That's the other angle. You can make a single particle bright enough. First, you can give a lot of excitation. Although the yield is low, you just strongly excite them. You can still make a bright particle. Second, you can increase the absorption, which is a common issue for a lot of doped nanoparticles. Absorption, yes, it is challenging. And the last one is the number of emitters. If you give a more number of emitters, you can dope thousands of them, 10,000 of them, 100,000 of them. You can make a single particle highly bright. So this is our strong belief, and when we started the experiment, the student synthesized, this is our basically the first batch of synthesized more than 10 years ago. We synthesized 0.2% to up to 8% of nanoparticles. And according to the textbook, if you dope the concentration of more than 2%, and everything will be quenched, right? Because the concentration concept. It's just true because when you measure from the suspension in the conditional spectrometer. But when you put this material inside of the suspended core optical fiber, where you have very strong concentration of light to excite your material, you found this concentration quenching can be overcome. You can turn on the brightness of 8% nanoparticle into very bright particles. And the mechanism behind this, we already published that. It's basically because you just keep filling the energy levels from ground state to the first level and the second level and third level. Then you can get more photon influx to the material so that you can pump the highly doped one into highly bright nanoparticles. In this case, we use the fiber, which is suspended core fiber, without any microscope. You're just using fiber and getting the concentration of particle low enough, you can very sensitively detect a single nanoparticle through the fiber, which is a very interesting application. And in parallel, we also drive the imaging because most of the application in the imaging area. So we put the nanoparticle under microscope and check what happened, okay? So because this is a very power-dependent phenomenon, means you need to give a strong power density. Means if you don't have a high-power laser, you just need to tightly focus your laser beam, right? So then you get this brightness of nanoparticle until you can see from the naked eye. Even when you turn on the transmission light, you see the single cell, and you can clearly see when this blue, each of the blue dots from the naked eye through the eyepiece, when they come into the cell, when they come out of the cell, this is a single molecule, the most simple way to do the single molecule detection and tracking the nanoparticles. The transfectional opportunity is you can move the traditional ELISA assay into single nanoparticle ELISA assay. Means each nanoparticle will label a molecule so that you can count the number of molecules, and which is quite important to detect early disease, like an early stage of the cancer. We also use this material to label the exosome. In biology world, there's a very hot word called exosome, which is a biological nanoparticles. So the question is, can we detect each single biological nanoparticle smaller than the diffraction limit using the synthesized nanoparticles? So in this case, you can see we can digitally count each of these exosome, the nanoparticle from the biology cell. And the sensitivity, you can see huge improvement from the traditional ELISA assay. So we already published this. I'll skip through very quickly. But when you want to do the imaging, we've got a little problem because each of the nanoparticle, they have their own diameter. When you label, even you do a very good labeling, you see this biological particle, which is soft, around 100 nanometer. Even you use a 20 nanometer nanoparticles. At most, you can label about 100 nanoparticles. It's quite hard to see the original shape or original morphology of the nanoparticle, which is still a challenging issue limiting this field, but we try everything possible in the lab. The next one, during the pandemic, what we do, at the pandemic, everything will stop, and we try to think how can we recover from the pandemic and what we can do as a research group. So before the pandemic, actually, I established a research center, which is targeting for the industry transformational research, means getting the material and detection technology for point-of-care detection. In this case, in Australia, we had 2 universities, 6 industry partners working together before the pandemic for 3 years until we got a lot of support from China as well, which is China-Australia development collaboration grants when they are good friends, not anymore. So we enjoy a lot of funding, and we develop a technique which we introduce the up-conversion nanoparticle as the fluorescent biomarker into the lateral flow strip. The strip we use for pregnancy test, we use for other sort of lateral flow test. And the idea is very simple. You know, we just want to use the new material in this existing platform. And we can use a mobile phone to detecting the results. And the result was great because the sensitivity of the material. After the pandemic, when the virus come, we carefully analyze the virus. Each virus only have 1 microRNA, but they have multiple proteins. They have about 1,000 nuclear protein. They have about 26 surface spike protein. So if you want to detect the virus quicker, you know, you have to using the antigen test. You know, but if you want to detect the virus more accurate, then you use the PCR test. You keep amplify the number of microRNAs. You know, but in our case, we wanted it quicker. We also wanted it more accurate. So what we do, we use this platform by replacing the gold nanoparticle by the highly doped nanocrystals, and you can see the control of the crystal is very precise. You can put a core shell structure, and you guarantee a very brightness of nanoparticles under the excitation. In the end, we developed this product they called visualizer, and the strip we call iStrip, and this is commercialized by a company in Perth, which is a saliva test. So you can collecting the sample from saliva, and you put into the lysyl buffer and put only 20 microliter of the sample into the strip. And after 5 minutes, you can read the antigen test results. But the process I want to emphasize is our capability in terms of getting the devices. And you can see this is the first one in the corner is a original device in the lab. And we make our optics match to their cartridge holder. And this is a detailed mechanical design. And we take this design and making the optics smaller and smaller until this size. And then we talk to the industry. They put into the laser safety box. You know, then this is first design. This is second generation of design, in which they make smaller, but you still need a computer or laptop to drive this. And the final product is about this big. So you build everything inside, and also this product can, this device can communicate all the data to the cloud, so that they can do remote sensing. The sensitivity is also great when we do the test, and of course, and a lot of independent tests after our work, and they prove, you know, this test is both accurate and quick. Okay, and you know, after pandemic, these days, since last year, nobody used antigen test, so we have to switch our focus to other applications. One application in Australia, you know, we care so much about our milk, you know, because the Australia and New Zealand is one of the, you know, biggest supplier of the milk, you know, particularly the infant powder formula to the children. But the problem is, because this brand milk they call A2, they are too popular. So the supply from the New Zealand and Australia, they're never enough. So they're collecting the milk everywhere in the world. But they don't, you know, they feel panic because they cannot guarantee this is the A2, you know, which the milk contains most of the useful proteins. So we developed a quantitative test for them, which they can use in, you know, for the collectors taking into the farm, so that we can quantify the number of useful proteins in their milk. Also, the other direction, you know, we collaborate with a hospital, and we use this test for preeclampsia test. And because this result has been published, you can download our paper. I don't need to go through too much detail. The other property, once we, as I said, when we come to this field, we love the fluorescence lifetime, because they have a longer fluorescence lifetime. Then we can apply all the tricks on the lifetime imaging and multiplexing in lifetime. And this is an old paper. I don't spend too much time. But in simple, you know, you can control the material. You can have the material to generate different cycle lifetime. And you can use this lifetime as a biomarker to label different analyze for optical multiplexing application, also the time result imaging application. The latest results, you can see we can generate different color, but each batch of the nanoparticle has different lifetime. And then you can multiplex. And you can even read the lifetime from a single nanoparticle, so that you can use the single nanoparticle to target different virus, the RNA oligostructure from a virus. You can do the single high throughput detection of the virus. Also, I truly believe there are plenty room at the bottom. Once you're getting smaller and smaller, you found a lot of opportunities. This is particularly true when you do the single particle characterization. We publish all the concept and the review a few years ago in Nature. We summarize what type of architect you have in terms of getting your material characterized at a single nanoparticle level. You can read our paper. This one, because the format, also the page limit we haven't published, you can take photo. I suggest. This one basically shows you how simple to put these optical Legos together so that you can characterize your single nanoparticle. In other words, you can have LEDs, some of the lasers, femtosecond laser at the light source, and you build IP fluorescent optics. You got stage, you got the cavity, and you also can use a variety of different cameras as your detector, and then you can assemble different type of single nanoparticle detection platform. This is exactly what happened in our lab. It's very messy, and there could be having some safety concern because you can see all the optics and components everywhere, and we're putting them together into the super resolution. In this case, is the STAT super resolution microscopy. We found if you do single particle characterization, you can switch on and off of single nanoparticle so that you can do super resolution imaging microscopy. This is also published. I'll glance through very quickly. This is some follow-on work. You found many nonlinear optical property from the single nanoparticle. And that drive to new optical imaging modality so that you can see each single nanoparticle very clear and with improved resolution under a microscope. This is all published. I can quickly glance through it. Nearly all the optical super resolution imaging optical modality we constructed in the past that works for the upconversion, and I'm pretty sure it will also work for other, downconversion or downshifting materials. The other one, we touch a little bit through this conference as well. You can use the lengthened phosphorus as the gain medium in the nanocavity and microcavity lasers. In this case, we demonstrate once you put a single particle on top of a microsphere, and that provides enough gain for you to achieve the lasing emission at a single nanoparticle level. These days, we've been using this material for optical cooling. This is laser-driven optical cooling, which you can cool down the localized temperature of the material. Also, the material has a very strong, independent of the environmental temperature, and this is something we published a few years ago. When the particle particularly getting small and you have the doping concentration of the ytterbium and thorium right, you can find you keep increasing the temperature, and this material can gain the brightness. Most of the phosphorus, when you increase the temperature, they drop the efficiency. But upconversion, they're doing a very different thing. So that you can use this temperature to cool down the material to enhance the material brightness. Also, you can develop a sensor, which you can, people call it nanothermometry in these days. We're interested in learning how much heat each mitochondria can generate inside the single cell. So in this case, you can label simultaneously in parallel mitochondria and the lysosome. The latest result from my lab, the student can also label the ER and Golgi these days. So we can simultaneously monitor the temperature change from the live cell. Also, you can see this is an optical tweezer setup in the lab. We try to grab a single nanoparticle. Can we control the single nanoparticle? Optical tweezer been Nobel Prize recognized twice in the past, but they haven't done any nanoscale tweezing because in the nanoscale you have a very strong Brownian motion that's very hard to do. In our case, we found once you highly dope a single nanoparticle upconversion, and you can generate a huge optical force compared to the Brownian motion. In that case, we can trap a single nanocrystal. And recently we also demonstrate this can be done inside the living cell, which is a new direction of the research. Control, the scale bar here is 50 nanometer, and you can imagine how many things we can do at this 50 nanometer scale, and how many different shapes or different elements we can dope into a single crystal. Once you can put into the single crystal, we can generate a nanoscale optical barcode, and you can manipulate all these optical properties within nanoscale, and to have a single crystal to emit white light, green light, blue light, and red light, all within the control. All right, the last topic is seeing through the tissue. This is a very hot topic over the last few years, I think a lot of phosphor community, they start to drive towards this direction because the near-infrared light can penetrate deeper through the tissue. In this case, you can see we also spend our energy and our focus on the instrumentation development. So the first two modality, which is relatively simple, the first one, we add a light sheet, means we put the excitation light thin enough so that we can check the tissue layer by layer. In that case, we can improve the resolution. The other one is we put in the time gating because most of this material, they have a longer lifetime so that you can improve the signal to contrast, to background contrast. Okay, so we also assemble this into our own instrumentation. We publish these results. And you can see this, can clearly see each of the blood vessel from under the small animal imaging facility, which we established by ourselves. One thing I really want to spend a little bit more time on these results, we published late last year. When you inject the nanoparticle into the circulation system, most of the time we believe, I talked to many people from the nanomedicine community, they believe the nanomaterial, if they are good, they can circulate and then get rid of the body through the urine, okay? If they are not good, they first accumulate into liver and the spleen and even kidney, and they stuck there for a little while before you can see anything from the urine. But there's a little time window people may overlook, which is from the circulation system. Our immune cell from the bone, they can uptake these materials from the circulation system because we know the bone and circulation system, they are connected, right? But because the immune cell from the bone system, they react very quick. They're slow, right? So they take nanoparticle also slow, and they remove nanoparticle also slow. But this is quite interesting because if you keep watch the live animal under the near IL-2 imaging system, you found maybe after a day or two, better at the 3 days after your injection, you see a lot of particles, they go to the bone system, okay? And this particle will be there not for days, not for weeks, but for months, okay? After 2 months, you can still find nanoparticle through the bone system, which provides you a new imaging opportunity because otherwise, if you want to image the bone, you have to use X-ray, right, which is dangerous. You cannot do it too often. But in this case, we can inject into the nanoparticle into the bone. I believe we only demonstrated the erbium doped yttrium nanoparticles. But I believe there will be a lot of other particles that will pass through this way, means circulation, the bone system, before they get rid of them from the urine system. In this case, you can see, we can clearly see the defect from the bone. We can also, using this technique to check the arthritics, You can see this is from the mice, and you can see when the arthritic kept happening, they have more immune cell in that region, and means the immune cell will take more nanoparticle in that region, so that you can easily see, very clearly see the joint. And in this case is synovitis diagnosed. You can see the nanoparticle, they have a very different behavior at the joint, okay, which provide a new way for you to check even the different kind of the bone diseases. Otherwise, you have to use micro-CT or X-ray. Okay, so this is, I think, is worth noting. Maybe if you have other nanoparticle or nanomaterials, you can check. Don't give away the mice after experiments. Leave them, for a couple of days or maybe a couple of weeks. Then you can see where the nanoparticle is, where they ended up. Okay. Of course, this is a system you can do in the digestion system as well in the near-infrared region. This is more result we published. This is something we recently published. We adding 2 cameras and 2 excitation wavelengths. 2 cameras can improve the resolution by about quarter two times. In the other 1.4 times the resolution. But once you can use the 2 lasers, you can use 2 types of different particles because one particle doped by neodymium, one particle doped by the erbium. The neodymium one is good for check the blood system, the circulation system. in the shallow skin, you know. But the erbium system, you can check the bone. In that case, you have two imaging modality, one 980, one 800, and then you can have you know, the two system checked using the same imaging system. In that case, you can do a lot of interesting, you know, deep tissue imaging. Because the time limit, I better stop here and by acknowledge all the contributions from my students and postdocs. I feel quite ashamed because most of the experiment, except my PhD results, was by myself, but most other results are done by my postdoc and student. Most likely, you know, from my collaborators. I'm just here to deliver the message. Thank you very much.
So thank you very much. So we have time for some questions. Are there any questions in the audience?
Thank you, Dayong, for a wonderful talk. And you say your nanoparticle can get into the bone. I think that's really interesting. But the issue is when generally when they get into the bone, not easy to come out. So is there concern for safety?
Yeah, there's safety still within the concern, and that's one of the most questions people ask at the conference. Lengthening material in general, they are safe, okay? Even the gadolinium ion we used for biomedical imaging. But the trick is you need to kill them. You need to wrap them, you know, by the organic structure. In terms of the nanoparticle, I think they are quite stable. When we also check the urine and also the facet after a few days, and all nanoparticles, they keep a very good, decent shape. You know, means they are not dissolved. So they can be removed from the body. So of course, if you getting smaller particle, it will be help because you can the particles spending less time in the circulation system. You can remove them quicker. But I think in general, it's I don't think this is a big concern compared to the dangerous X-ray.
Any other question? I have a small question. Yeah. When you had your particles highly doped with thulium, was it not an avalanche effect, in fact, that you were seeing at that time?
No.
It was also
you can dope any concentration, particularly at nano scale. A lot of things, a lot of thulium dope I know in the microparticles. You cannot increase the thulium too much because otherwise the crystal will break. But in nanoparticles, there's no limitation.
Okay. Thank you. So I think now we have to close the session. But before, since it's the last section, maybe we can thank the organizer as well as students and all people that arrange the conference. I think we can make a good applause for them.
Thank you very much. Okay. So I think it's the Phosphor Safari is the 2024. It's close the end, and everybody is very interested for next the place for the hold this the Phosphor Safari in 2026. So now is the next chairman is to stay here. So it's my honor to invited Professor Jin to briefly introduce in the future plan for the Phosphor Safari. Okay, thank you.
Thank you. This is a huge task. I feel more and more nervous because particularly when I see the quality and the standard of this conference, I can only say I'll try my best, okay, to do the best I can do and with my team. But please mark your calendar. I fixed the date, 22nd to 25th of February. If that doesn't happen, it should happen within that date, around that day, because I haven't confirmed the venue. But let's fix the date, because I checked the calendar, 17th of February is a Chinese New Year. So the reason I put a little bit later after the Chinese New Year, I really want to invite you and your family to spend Chinese New Year, a summer, warmer Chinese New Year in Australia, okay? So February is our typical season. It's in summer, but not too hot, not very hot, not like here, okay? Typically January. January is very hot, but the end of February, the temperature cool down a bit, but you can still swim, you know, on the, within the ocean. So that's a very pleasant season in Australia. Coincidentally, around that date, there's every 2 years, there's a conference called Nanoscience and Nanotechnology, which is Australian version of Nanoscience conference, but every 2 years, which is a big conference. And also in Sydney, because the reason I know that I'm one of the symposium chair for that conference. So I can bring the two things together. If, at your choice, if you want to attend more science event, please. Otherwise, one conference and plenty time for you to take a rest in Sydney. Yes, that's in Sydney, and you know this is normal for us because we take this sort of image every day. Our beach, definitely, this is exactly in the summer. You know, in February you will see this. You know, this is nothing AI. You know, it's real. Okay, it's a real photo. Okay, it's a real photo. Kangaroos, of course, our friends. Koalas, yeah, and emu, yeah, a lot of animals, and they are very friendly. Okay. The location, yes. As I said, my university at the middle of the Sydney, so it took about 2 minutes from my office to Central Station, right? 5 minutes to Chinatown. And if you land in airport, we plan to build a new airport, but it has to be in 30 years' time, okay? But you have to use the old airport. But the good advantage is this old airport only take about 15 minutes by high-speed train from the airport to the campus. So very convenient. Every evening at Darling Harbour, you will see the fireworks. You know, this is something I can guarantee. Okay. The university, yes, we are one of the top 100 university. Most likely, we will have the conference on campus because it's cheaper. Okay. This is what happened last June. So we had a tradition to organize the IBMD Research Week. In that week, we have a different kind of conference and activities. So I try to concentrate everything so that people have more flexibility so that you can attend other events as well, because it is a multidisciplinary research and more so that you can enjoy the different topics. And this is exactly what happened you know, last year, you know, 12 months ago in Sydney. Yes, I'll treat you well, and this is what happened in June, because you can see in this season we are in winter. But we bring the guests on the boat, so I try to organize a boat for you on the Darling Harbour. I sort of can guarantee this, but I cannot promise. Depends on whether, of course, food. So as a country with a multicultural, so we have plenty of different combination with the food, like European food, Asian food, you know, Chinese food, Japanese food, you know, Korean food. We have 2 Korean towns in Sydney. You know, very easy to find, and multiple Chinese restaurants as well. Yeah, please remember this. Okay, welcome to Australia. Okay, to some of my friends, I will say you must come. Okay, thank you.
So now we have the 10 minutes for the coffee break. Okay, just go back soon.
See you next time.
现了。
走吧。送到门口。
OK。
像名字对掉地了。哦，没有啊，就是要高灯。除了柜台之外的所有东西。
Ladies and gentlemen, good afternoon. The closing ceremony will begin in 5 minutes. Please take your seats. Ladies and gentlemen, welcome to the closing ceremony. First, let's listen to a closing ceremony. Let's listen to closing remarks from our symposium chairman. Please welcome Professor Chunjie Lin, an associate professor from the Department of Molecular Science and Engineering at National Taipei University of Technology.
Okay, good afternoon, ladies and gentlemen. I think it's the 3 days passes very quickly. So it's my honor to successfully finish my dream. Okay, and I needed to thank a lot of the participants. Okay, Professor Ruxi Liu, Professor Andrew Marink, and Professor Toda, and all my colleagues. And all of the powerful for my students, okay? So I am very happy to invite all of my friends to visit Taipei. I think it's very deeply the memory for everybody. So now I just want to give everybody the last gift, small gift. It's all the 3 days, sounds very specific, the memory, the video. Please enjoy.
Thank you, Professor Lin. And now we will proceed with the award presentation segment. The following award order is arranged according to the serial number. First, we will present the award for the winners of the oral presentation. The awardees are Andrew Tushatov, Lin Chunjian, Loganathan Varamoto. Please give a warm round of applause to congratulate them. And now, please welcome Professor Kenji Toda to present the award. Congratulations. And next, and the second awardees are Archina Pondian, Yawala Tariwan, Nuante Wantana. Please give a warm round of applause to congratulate them. And please welcome Professor Xiaojun Wang to present the award. Congratulations. And now, we will present the award for the winners of the poster presentation. And the one round of awardees are Guanzhong Chen, Wesley Conham, Wadam Hikita. Please give them a warm round of applause to congratulate them. And please welcome Professor Andrei Suhosky to present the award. Congratulations. And the second round of awardees are Yiting Lai, Wenzhe Huang, and Jingyang Wu. Please give them a warm round of applause to congratulate them. And please welcome Professor Andrzej Suchalski to present the award. Congratulations. And the last round of awardees are Jonghyun Yu, Rio Ono, Mohammed Muntazia. Please give them a warm round of applause to congratulate them. And please welcome Professor Lucy Liu to present the award. Take a photo, please. Congratulations. And now, last but not least, we are delighted to welcome Professor Andres Maring to give remarks for ending this symposium. Thank you, ladies and gentlemen. Thank you, attention. And please welcome Professor Maring.
Maybe a little lower, yeah, that could be good. Does not seem to Okay, thank you. It always works better when you turn it on, just as with equipment. Yes, so I've been asked to say a few closing remarks. So I made a little PowerPoint in which I reflect on this conference. So it's sad that we've come to an end to an exciting and I think very successful Phosphor Safari. So thank you and goodbye. And I could leave it as that, but maybe it's good to also reflect on what makes a conference successful. Well, the most important things are the participants. And we had lots of participants, but I did not have a list, I did not count, but I think we had about 120 participants and many participants from all over the world. Sadly, we missed many good friends from China. They could not come. And they are a very important part of our strong luminescence community. But fortunately, many of them could join online. So we had some online presentations from Professor Sato, from Professor Sun, from Xiaogang Liu. And I'm very glad that they could do that and still be part of this conference. Because traditionally, the Chinese luminescence researchers are a very strong part of our community. And also I know that many of them followed the conference online. And the editor of the Journal of Luminescence, Xiaogang Chen, he sent me a little WeChat message and he said, nice talk. Oh, it's nice. And he showed some pictures. So I also know what they saw and I think it was really nice. They could follow it very well. They could see the slides and see the presenter, and also when questions were asked, they could follow. So I appreciated that. Thank you, Professor Chen, for sending that. So, what else makes a conference successful? I think also having good presentations, plenary lectures, keynote lectures, invited lectures. And I think we have special thanks for the excellent lectures by the plenary lecturers, Professor Peng, Professor Adachi, Professor Liu, Professor Chu, Xiaogang Liu, who presented it online, Professor Zhu, Professor Fang, Dr. Sun, and Dai Yin. And yeah, I just have 2 of the pictures because the movie didn't have those yet, so I thought I would include them because those were just given this afternoon. So wonderful, 8 plenary lecturers. There may be something that you notice when you look at the 8 plenary lecturers. They're all men. Or at least they all identify as men as far as I know, to say it completely politically correct. And if you look at the International Advisory Committee, I think 70% of those, and only Ling Dong-soon is a woman, as far as I know, and the rest are all men. So I think we have a job here in our community to do. And that was also noticed yesterday. Professor Su chaired the women's session, where there were all female and 1 male speaker. She did study the program very carefully, and she calculated that there is 16.5% of presentations were by women, and the rest was all by men. So I think that's something to think about for the next Phosphor Safari, the one in 2026. Maybe we should add some female members to the International Advisory Board. I think that will be very good. And I think some of the women speaking in that session and the women chairing that session could be really good additions to the International Advisory Board. And also I think we could increase the number of female plenary lectures by infinite percent. I mean, you explained the symbol and it has many different meanings, but it also means infinite. So that means also that the conference will go on infinitely. So that's a nice task for our new chairman. And I hope that somebody can pass on the message, because he just left. He's flying back to Sydney. But I think it's really important that we do include more women in the plenary and the keynote and invited lectures. That is really important. And I think Professor Tode gave a very good example. Probably 20 years ago, we would have said, if your wife permits it, but he very politically correct said, if your wife or husband permits it. Also acknowledging that there's many women scientists in our community now. So what else makes a conference successful? I think diversity, another politically correct word, but with diversity I now mean that we had a very large diversity in our topics. There were different systems, organic, inorganic, biological materials, different types of luminescent species, quantum dots, pi-pi-tar transitions, lanthanized transition metal ions, nano, microcrystals, and a wide range of applications. And this is not all of them: solar cells, LEDs, imaging, sensing, OLEDs, afterglow, plant growth, medical, micro-LEDs. And I've really learned a lot here. I think that also helps. We're not a very focused meeting. We cover all kinds of luminescence phenomena, luminescence material, and luminescence applications. What's also very important is that there's active discussion. And I found that after many talks, there was a lot of time, there were a lot of questions asked. There was often not a lot of time for questions, because speakers tend to run a little late, but there were a lot of questions asked, and here you can see just some of the people asking smart questions. Also very important is interaction with young people, and they typically present posters. So there was I think, a very nice poster session. It's a good opportunity for young people to really interact and to talk with the, I shouldn't say old people, but the experienced scientists. But there were many interesting posters that I missed, because sadly I had other obligations. Professor Liu is a very demanding host, so he had planned a nice program for me. I did not just skip. If you missed me during some presentations, I wasn't just being lazy. I gave a lecture at the NTU on Wednesday afternoon, then at the College of Biomedical Science and Engineering on Thursday morning, and then we had a wonderful guided tour at Professor Lucy Liu's lab at the late afternoon, so I missed the poster session here, and that is sad. But Dr. Chen was a wonderful host for my visit to the College of Biomedical and Science Engineering. And here I'm presenting at the NTU, showing them luminescence. And this was the lab tour, also very interesting. Professor Liu has a very well-equipped lab, crammed in very small space. Also the students don't have a lot of space. And also was very interesting to see all the objects in the cupboards of Professor Liu. I think I could study that for months. So that was really interesting and good, but that makes it I did miss the poster session. What else? I also liked the technical exhibition. I talked to many of the people who have new products, the nice microfluidic reactors from Great Britain I found really interesting. Also this I really liked from Ocean Optics. This is their typical CCD spectrometer. They have a very cute little new spectrometer. And I asked the lady, what is the technique? And I said, it's not CCD based, but it's secret. So I feel like buying one and taking it apart to find out what's in there. But it's nice to be introduced to new technology during the technical session. Also, I think there was a very good representation of companies working on light emitting materials. You saw a beautiful presentation on micro-LEDs, but also Cibro was there, many other companies were there, and I think that is very important, that I'm from academia, that we interact with people from the industry, the real world, and get inspired with the problems they face that we may be able to find solutions for. So here more booths. There was really a lot of interaction and attention for this technical exhibition. Yeah, then of course, very important, the social interaction. And that's, I think, something that we really missed during the Corona times. We were not able to enjoy this part of science, getting together, interacting socially, and also scientifically discussing and being together as a community. And yeah, social interaction, good food, culture, music, fun activities. And it already started before the conference when Chun-Che honored his, what in German is called Dr. Vater. You have your real father, but then scientifically you also have a father. In German it's called the Dr. Vater. And Chun-Che really gave a very nice speech in honor to Rushi Liu. And yeah, it was a beautiful cake, not easy to cut. He did a great job with this little plastic knife. Very impressive. And then also Rushi said some nice words. So that was before the meeting really started. And then, yeah, yesterday we had the conference banquet. And yeah, I had a wonderful time. It was a great organized event. So thank you for organizing that. I always love it to interact with the students in a different way, seeing my colleagues again. So, and also the food was delicious. So, happy students, happy me. Delicious food. I love sashimi, and I could just pile it up as much as I liked. I think the students did as well. And then there was very special music. And also the cousin of Chun-Che. And that should be a movie. I don't know if it will play. Will it play? Yes. There is sound. I said I was very sorry there is no sound. He had a wonderful voice. I really enjoyed his music. Yeah, and I thought I would do it with my laptop and then there would not be sound, but yeah, so there is sound. And again, here there should be sound. So students cheering for the supervisor, Chun-Che. And that's of course very nice. What is not so nice is Marianne's comment, because she was a student in my group. She said, why don't your students do that for you? I guess I'm not as popular as Chunche. But yeah, I really like that. I think the students had a great time. We all had a great time. Yeah, then more memorable karaoke. Maybe not so sorry there is no sound. I'm not sure if we should play this. But we can, because this is also a movie. I guess Chunche has different genes than his cousin. But it was fun. I really enjoyed it. Let's stop that. So then, yeah, what really makes conference successful is the students. I think the students here, they were very helpful. They did a great job organizing. They met you at the registration desk. They had all those signs so you would not get lost on the path from the hotel. They nicely guided you to where you had to be. They also kept track of the time, ringing the bell, sometimes keeping ringing the bell, and then the speaker would continue speaking, ignoring the bell, but the students did their best, and also the 1 minute signs, then also the food and the drinks, so that is really highly appreciated. Also maybe the staff, we had those beautiful decorations, which I learned were by the chairwoman, Amber. She made all those beautiful decorations. And also if there are technical problems, the students solve them. So I think it's good to give a big hand for the students and all the support staff. Yeah, and what makes conference successful? Of course, the chair and the co-chair. And Rushi told me, I did 2% of the work, Chunche did 98% of the work. But yes, thank you very much for organizing a wonderful Phosphor Safari. I've really enjoyed it. You've worked really hard and you made it a great success. So, even a bigger hand for the chair and the co-chair. Thank you very much. Yeah, then have a nice trip back home. That's what I usually say at the end of a conference. And see you in 2026 in Sydney. But this conference is different because I hope to see you tomorrow. And then we will do many wonderful things, but we will also visit this wonderful geopark. And you can imitate this picture because that is where this picture is taken. With that, I'd like to thank again the students, the staff, the organizers. I had a wonderful conference and I look forward to the next one in Sydney. Thank you. Oh, and then, yes, Chunche said, please, all the students, come to the stage. All the staff, support staff, students, because you've done a great job. Please come to the stage.
So we would like to thank all your attending this conference, and thank you for coming. And we also hope you safely back to your home. Thank you very much, and see you in Sydney in the year of 2026. Thank you very much. Okay, bye-bye. Congratulations.
Thank you. You did a great job.
Yeah. 好，谢谢各位同学，谢谢。